Hey there, how's it going? Thanks for joining me today. Whether you're relaxing at home, on your commute, or winding down for the evening, I'm really glad you're here. August 30th, 2019. Something impossible happened. An automated telescope system in Hawaii, one of two identical instruments scanning the sky night after night, captured an image that would change everything. The Atlas survey, designed specifically to hunt for dangerous asteroids that might threaten Earth, flags objects constantly. Thousands of dots appear in the data every night. Most are familiar. Known asteroids following predictable orbits, distant stars that happen to line up with the camera's field of view, the occasional satellite passing through. This dot, just another entry in the night's catalogue. Nothing remarkable, not yet. Before we continue this journey, tell us where you're tuning in from, and if this story resonates with you, make sure you're subscribed because tomorrow I've saved something extraordinary for you. But 4 days later, something remarkable happens. Halfway around the world, in Crimea, an amateur astronomer makes a discovery. His name is Gennady Borisov. He's not working with billion-dollar equipment or teams of researchers. He's using a telescope he built himself, piece by piece, in his backyard. A labor of love constructed from carefully selected mirrors, lenses, and mounting hardware. On the night of September 2nd, he's doing what he loves, scanning the sky, looking for anything unusual. And there it is, a faint smudge moving against the background of stars. He notes its position carefully. He tracks it. He reports it to the Minor Planet Center, the international clearinghouse for observations of asteroids and comets. Within hours, astronomers worldwide receive the notification. Something new has been spotted. They point their telescopes at the coordinates Borisov provided. They capture their own images, their own measurements. The calculations begin. And that's when the numbers start refusing to cooperate with reality. Here's what you need to understand about orbital mechanics, the mathematics that govern how objects move through space. Everything in our solar system follows strict rules defined by gravity and velocity. The Sun sits at the center, its massive gravitational pull reaching out across billions of kilometers, holding everything in its grip. Planets orbit in near circles. Asteroids trace ellipses. Comets swing through on stretched, elongated paths that carry them far beyond Pluto before bringing them racing back toward the inner solar system. But they always come back. The mathematics guarantee it. These objects are trapped, gravitationally bound to the Sunday. They're part of our solar system's family, and they're here to stay. The key number that describes an orbit is called eccentricity. Think of it as a measure of how stretched out an orbital path is. A perfect circle has an eccentricity of exactly 0. Earth's orbit is nearly circular, with an eccentricity of just 0.017. We trace a path around the Sun that barely deviates from a perfect circle. Halley's Comet, that famous visitor that swings past Earth every 76 years, has an eccentricity of 0.967. Its orbit is dramatically elongated, stretching far out into the outer solar system before plunging back toward the Sunday. But even Halley's Comet is trapped. It always returns. The boundary between trapped and free is eccentricity of 1.0. Below that number, you're bound to the solar system forever. At exactly 1.0, you're on what's called a parabolic trajectory, moving just fast enough to escape the Sun's gravity, but barely. Above 1.0, that's called a hyperbolic orbit. You have excess velocity. You came from somewhere else, and you're leaving. You're not part of this solar system at all. The astronomers calculating the trajectory of Borisov's object run the numbers once, then again, then a third time. They check for errors. They verify their measurements. Other observatories confirm the position data. The International Astronomical Union's Minor Planet Center runs its own calculations using their sophisticated orbital determination software. Everyone gets the same answer. Eccentricity, 3.3. That single number changes everything. This object didn't originate in our solar system. It came from somewhere else, from another star, from interstellar space, from the vast darkness between stellar systems. It's passing through our neighborhood like a traveler on a highway, here briefly, then gone forever. The sun's gravity will bend its path slightly as it swings through, but it won't capture it. Nothing can slow it down enough to trap it here. This visitor is just passing through. And here's the truly staggering part. In 4 billion years of Earth's existence, in all the millennia that humans have watched the sky, we've only definitively identified one previous interstellar object passing through our solar system. Just one. It arrived in October of 2017. We named it Oumuamua, a Hawaiian word meaning scout or messenger from the distant past. That object sparked enormous excitement and controversy. Its shape was unusual, elongated, tumbling. Its trajectory showed unexplained acceleration that couldn't quite be accounted for by natural processes. Some scientists suggested it might be artificial, a light sail from another civilization perhaps. Others insisted it was simply a comet with unusual properties. The debate never fully resolved because Oumuamua left before we could study it properly. It was discovered after it had already passed closest to the sun and was racing outward, getting fainter every day. We caught only a glimpse before it vanished into the darkness. Now, just 25 months later, we've spotted another one. 2 interstellar objects in 3 years, after 4 billion years, of none, or at least none that we detected. The astronomical community lights up. Email chains spread the news within hours. Observatories around the world scramble to reorient their instruments. Every major telescope that can possibly observe this object adjusts its schedule. The urgency is absolute. Unlike asteroids that orbit predictably for centuries, unlike comets that return on schedule, this object will pass through once and never return. Every observation matters. Every measurement counts. There's no second chance. Miss this opportunity, and it's gone forever. They give it an official designation, 2I/Borisov, where the I stands for interstellar. Later, it gets redesignated as 3I/Atlas, acknowledging both the Atlas survey system that first detected it and Borisov's independent discovery. But most people simply call it by Borisov's name, a recognition of the amateur astronomer who spotted something extraordinary. As telescopes focus and data starts accumulating, something else begins to happen. Beyond the scientific excitement, beyond the thrill of detecting a genuine interstellar visitor, whispers start circulating. Quiet conversations at conferences, careful emails between colleagues. Not public speculation, not yet, but private questions. What if this wasn't random? What if the timing isn't coincidence? What if something sent it? What if we're being tested? The questions sound like science fiction. They sound like the kind of speculation you'd dismiss immediately. But here's the thing. The people asking these questions aren't conspiracy theorists or UFO enthusiasts. They're professional astronomers. People who've spent their careers studying orbital mechanics and stellar formation and the statistical distribution of objects in space. And some of them are looking at the numbers and feeling uncomfortable. Think about the probability. We've been studying the sky seriously for centuries. We've had powerful telescopes for decades. We've had automated survey systems specifically designed to detect fast-moving objects for years. And in all that time, nothing. No confirmed interstellar visitors. Then suddenly, within just 3 years, we detect 2. Either our previous estimates of how common these objects are were catastrophically wrong off by factors of hundreds or thousands, or something unusual is happening. Either interstellar space is far more crowded with wandering objects than we ever imagined, or these particular visitors aren't random samples from some background population. they're something else. And here's what makes the speculation particularly intriguing. We just developed the technology to detect these objects reliably. The ATLAS system that caught 3I/Atlas came online in 2015. The Pan-STARRS survey that discovered Oumuamua became fully operational in 2014. For the first time in human history, we have the capability to spot interstellar visitors as they pass through. We crossed a technological threshold. We can see what we couldn't see before. And immediately, almost as if on cue, the visitors start appearing. If you were an advanced civilization watching developing species across the galaxy, wouldn't this be exactly the moment you'd want to test them? The moment they become capable of detecting interstellar objects? The moment they can distinguish a visitor from another star system from their own local comets and asteroids? If you wanted to measure their technological capability without revealing yourself, without making obvious contact, wouldn't you send something right at this threshold moment? It's speculation, of course. Wild speculation, even. The far more likely explanation is natural, that interstellar objects are simply common enough that we're now detecting them regularly, and the timing is pure coincidence. That's what most scientists believe. That's certainly the simplest explanation. But the questions linger, because once you notice the pattern, once you see how the timing lines up so perfectly with our detection capability, it's hard to unsee it. It feels orchestrated. It feels like a test. For thousands of years, humanity assumed our solar system was isolated. A bubble of gravitationally bound objects surrounding our sun, floating through empty space, separated from other stellar systems by vast, uncrossable distances. The space between stars was void, empty. Nothing travelled those immense distances. Each star system was its own private island. Then we developed better technology, better telescopes, better detection systems, and suddenly we're not isolated at all. Material flows between the stars constantly. Rocks ejected from planetary systems during their chaotic formation, ice scattered by gravitational interactions, debris flung into the galaxy during stellar close encounters. The space between stars isn't empty. It's full of wanderers, objects drifting through the darkness, occasionally passing through stellar systems like ours. And if natural objects travel between stars, then why not artificial ones? If matter flows through the galaxy, why couldn't intelligence harness that flow? If we're already planning missions to send tiny probes to nearby star systems, projects like Breakthrough Starshot that aim to reach Proxima Centauri within decades, then why wouldn't other civilizations, perhaps millions of years ahead of us, have already done this? The test hypothesis emerges not from paranoia or wishful thinking, but from simple logic. We develop detection capability. Visitors immediately appear. Either that's coincidence, or it's not. Either we're alone in watching the cosmos, or we're being watched. Either these objects are natural wanderers following the random paths of gravitational ejection, or they're something more purposeful. We don't know the answer, not yet. The data we collected from 3I/Atlas doesn't prove either explanation. It leaves both possibilities open. And that's perhaps the most fascinating part of this story. We're at a threshold, not just technologically, but conceptually. We're asking questions that would have been dismissed as unscientific just a decade ago. We're designing observation programs to test hypotheses that sound like they belong in science fiction. This opening moment, August 30th, 2019, when an automated telescope captured something impossible, represents more than just a scientific discovery. It represents the moment humanity realized the universe might be far stranger, far more populated, far more purposeful than we ever imagined. Before we had the tools to detect interstellar visitors, we were blind. We couldn't see them. They could have been passing through our solar system for millions of years, and we would never have known. Now we can see. We've crossed that threshold. We're watching. And what we're seeing, doesn't quite fit the comfortable patterns we expected. The timing is too perfect, the frequency too high, the coincidences too aligned. Something's different. Maybe it's natural. Maybe our models of the galaxy were simply incomplete, and we're now updating them to match reality. Or maybe, just maybe, we're not alone in watching the cosmos. Maybe we're being watched in return. Maybe these visitors aren't random at all. Maybe they're tests, sent to measure our capability, to assess our readiness, to determine if we're advanced enough to notice. Either way, everything changes from this moment forward. We can't unsee what we've seen. We can't stop wondering what these visitors truly are. We can't stop watching for the next one, because it's coming. Somewhere, out there, in the darkness between stars, another object is already traveling toward us. We don't know when it will arrive. We don't know what it truly is, but we know we'll be watching. We know we'll be ready. The story of 3I/Atlas, the stranger that changed everything, is just beginning. And as you'll discover in the coming chapters, the deeper we look into this mystery, the stranger and more fascinating it becomes. The universe just got a lot more interesting, and we're only starting to understand what that means. To really understand what makes 3I/Atlas genuinely strange, to appreciate why it sparked those whispered questions about tests and purpose, we need to step back and understand something fundamental. We need to understand the invisible architecture that holds our solar system together, the mathematical cage of gravity that defines what's possible and what's not. Picture the sun as a massive drain in the fabric of space itself. That's not just a metaphor. Einstein showed us that massive objects literally bend space-time, creating wells that other objects fall into. The sun, containing 99.8% of all the mass in our solar system, creates an enormous gravitational well. Everything nearby wants to fall inward, pulled by that relentless attraction. But here's the beautiful thing. Objects don't fall straight in. They have sideways velocity orbital motion that keeps them circling instead of crashing. It's a perfect balance. Earth, for instance, orbits the Sun at approximately 30 kilometers per second. That's over 67,000 miles per hour. At that precise speed and distance, the inward pull of gravity exactly balances the outward effect of our motion. We trace a nearly circular path around the Sun, neither falling in nor flying away. We're trapped, but it's a stable trap, a comfortable orbit that we've maintained for 4.5 billion years. Comets follow the same rules, just with different geometries. They swing through on stretched ellipses, elongated paths that carry them far beyond the orbit of Pluto, out into a region called the Oort cloud, where billions of icy bodies drift in the Sun's distant embrace. Then gravity pulls them back, and they plunge toward the inner solar system, picking up speed as they fall inward. They whip past the Sun at tremendous velocities, then climb back out, slowing as they fight against gravity's pull. But they always return. The mathematics guarantee it. Once you're gravitationally bound to the Sun, you're part of the family. You're here to stay, unless the mathematics break. There's a specific number that describes the shape of an orbit. We call it eccentricity, and it tells us everything about how an object moves through space. Let me walk you through this, because understanding eccentricity is key to understanding why 3I/ATLAS is so extraordinary. An eccentricity of exactly 0 describes a perfect circle. Every point on the orbital path is the same distance from the Sunday Earth's orbit, is nearly this perfect we. We have an eccentricity of just 0.017. If you drew Earth's orbit on paper, you wouldn't be able to see the deviation from a perfect circle. It's that close. As eccentricity increases, orbits become more elongated. Mars has an eccentricity of about 0.09, 3 still nearly circular. Jupiter, 0.049. Even the gas giants trace paths that are almost round. But comets? Comets are different. Halley's Comet, that famous visitor that passes Earth every 76 years, has an eccentricity of 0.967. Its orbit is dramatically stretched, carrying it from the inner solar system out beyond Neptune before bringing it back. Still bound, still returning, but on a path that's barely recognizable as an ellipse. It's elongated almost to the breaking point. The breaking point is eccentricity of 1.0. This is the boundary between trapped and free. Below 1.0, you're gravitationally bound to the Sun forever. You might take centuries to complete one orbit. You might swing out to unimaginable distances, but you will return. The Sun owns you. At exactly 1.0, you're on what mathematicians call a parabolic trajectory. You're moving, precisely fast enough to escape the Sun's gravity, but only just. You'll never return, but you'll also never pick up any extra speed. You're on the knife edge between trapped and free. Above 1.0, that's where things get interesting. That's called a hyperbolic orbit, and it means you have excess velocity. You're not just escaping, you're escaping with speed to spare. You came from somewhere else. You arrived with velocity that didn't originate from falling toward our Sunday. You're an outsider, a visitor, fundamentally not part of our solar system. When the first calculations came back for the object Borisov discovered, the number was impossible to believe. Eccentricity, 3.3. Let me emphasize what that means. Not 1.1, which would indicate barely enough excess velocity to escape. Not 1.5, which would be unusual but perhaps explainable by some complex gravitational interaction. 3.3. That's more than triple the escape threshold. This object wasn't just leaving our solar system, it was racing through with velocity that could only mean one thing. It came from another star. The astronomers double-checked everything. They verified the position measurements. They confirmed the velocity calculations. They ran the orbital determination software multiple times. Other observatories captured their own images, their own data points. The International Astronomical Union's Minor Planet Center, the organization responsible for tracking all the small bodies in our solar system, ran its own independent calculations. Everyone got the same answer. No matter how they approached it, no matter what methods they used, the mathematics was unambiguous. This object originated beyond our solar system. It had been traveling through interstellar space for who knows how long, hundreds of thousands of years, perhaps millions before its path happened to carry it through our neighborhood. Here's what the trajectory looked like. 3I/Atlas approached the Sun from above the ecliptic plane. That's the flat disk where the planets orbit. It came in at an angle, crossing down through the plane, heading toward its closest approach to the Sunday. That closest point, called perihelion, occurred on December 8, 2019. The distance at perihelion was approximately 2 astronomical units. An astronomical unit is the distance from Earth to the Sun, about 150 million kilometers, or 93 million miles. 2 astronomical units puts perihelion roughly at the orbit of Mars. Close enough to receive decent sunlight, close enough for detailed observations from Earth, but far enough to avoid the extreme heating that would vaporize a comet passing very close to the Sunday. After perihelion, the object swung back up, crossing through the ecliptic plane again as it departed. The Sun's gravity bent its path, but not enough to capture it. The object maintained more than enough velocity to escape. It departed our solar system heading in a different direction than it arrived, its path altered by the Sun's gravitational influence, but still fundamentally on an escape trajectory. The mathematics are beautiful, precise, unambiguous. They tell us exactly where this object came from, not which specific star system. The uncertainties are too large for that, but the general direction in interstellar space. They tell us its velocity, they tell us its future path, and they tell us, with absolute certainty, that this visitor is not and never was part of our solar system. But here's where the story gets strange. Here's where the comfortable mathematics start raising uncomfortable questions. The first anomaly is trajectory distribution. If interstellar objects are randomly wandering through the galaxy, following paths determined by their ejection velocities and chance gravitational encounters, then they should arrive at Earth from random directions. The celestial sphere, the imaginary, the sphere of the sky surrounding Earth has no preferred zones. Every direction should be equally likely. An interstellar object could approach from above the solar system's plane, below it, from any angle in between. The inclination, the angle at which a trajectory crosses the ecliptic plane, should be uniformly distributed. Yet both Oumuamua and 3I/Atlas arrived through relatively similar trajectories. Both crossed through the ecliptic plane where planets orbit. Both approached at inclinations between 20 and 50 degrees, rather than the steep angles of 70 or 80 degrees that are equally probable for random arrivals. With just 2 data points, we can't calculate precise statistics. But imagine throwing darts at a sphere from random positions in space. The sphere's surface has equal area everywhere. The probability of hitting any particular region is proportional to that region's area. Now, throw 2 darts. What are the odds both land in similar regions, similar angles, similar orientations? The probability isn't 0. Coincidences happen, but it's low enough to make you wonder. Then there's the timing issue, and this is where things get really uncomfortable. Astrophysicists had been thinking about interstellar objects for decades before Oumuamua's discovery. The theory was straightforward. Young star systems are chaotic places. Planets form, migrate, interact gravitationally. Some of those interactions are violent enough to fling smaller objects out of the system entirely. Over billions of years, as star systems age and settle into stable configurations, they should collectively eject enormous numbers of objects into interstellar space. The galaxy is over 13 billion years old. It contains hundreds of billions of stars. If even a small fraction of those stars have planetary systems, and we now know most do, and if even a small percentage of those systems eject material during formation, and physics suggests this should be common, then interstellar space should contain a background population of wanderers, rocky asteroids, icy comets, debris of every description drifting through the darkness, following ballistic paths determined billions of years ago by long-forgotten gravitational encounters. But how dense is that population? How many of these wanderers exist per cubic light-year of space? And crucially for us, how often should we expect one to pass through our solar system close enough for us to detect it? Before 2017, astronomers had calculated estimates. They used models of stellar formation, gravitational ejection rates, and the expected distribution of object sizes. They factored in our detection capabilities, how sensitive our telescopes are, what size objects we can spot at various distances. They ran the numbers. The predictions were consistent. We might detect 1 interstellar object per decade with our current technology, maybe 1 per century. Conservative estimates went even lower, perhaps 1 every few centuries. These objects should be rare, at least as far as detection goes. We should have to wait patiently, watching for years or decades, before catching one. Then, Oumuamua appeared in October 2017. Excitement swept through the astronomical community. We'd finally detected one. After years of theoretical predictions, we had actual observational confirmation that interstellar objects pass through our solar system. It was a milestone proof that the models were fundamentally correct, even if the exact detection rates needed refinement. Then 3I/Atlas arrived in August 2019. 25 months. Just over 2 years between detections. The models were clearly wrong, but wrong in which direction? Either the background population of interstellar objects is far denser than predicted, Perhaps by factors of hundreds or thousands, or something else is happening. Maybe the ejection rates from young stellar systems are much higher than models suggested. Maybe the galaxy is just naturally more crowded with this debris than we thought. That would be fascinating scientifically. It would tell us something important about planetary formation and stellar evolution that we didn't previously understand. Or maybe these particular objects aren't random samples from some background population. Maybe they're not following the statistical distribution we'd expect from natural ejection and billions of years of random drifting. Maybe there's something else going on. We just happen to develop the technology to detect these objects. Sophisticated automated survey systems like ATLAS and PanSTARRS, and immediately, within just 3 years, we spot 2. After millennia of human stargazing and decades of modern astronomy detected none, the coincidence is striking. Now let's look at the object itself, the physical characteristics that made 3I/ATLAS both familiar and unsettling. The Gemini North Telescope in Hawaii started capturing spectroscopic data in September 2019, shortly after the object's interstellar nature was confirmed. Spectroscopy is one of astronomy's most powerful tools. You take the light from an object and split it into its component wavelengths, essentially creating a rainbow. Different chemicals absorb and emit light at specific, characteristic wavelengths. By analyzing which wavelengths are present or absent, we can determine what something is made of, even from billions of kilometers away. The spectrum from 3I/ATLAS showed familiar features: water ice, cyanogen gas, a simple molecule made of carbon and nitrogen, diatomic carbon, 2 carbon atoms bonded together. These are all standard comet materials. Exactly what we'd expect from icy bodies in our own solar system. The Very Large Telescope in Chile, actually 4 8.2-meter telescopes working together as an interferometer, confirmed similar findings. The Hubble Space Telescope captured images showing a classic cometary coma, a fuzzy cloud of sublimating gas surrounding the solid nucleus. As the object approached the Sun, solar heating was vaporizing the surface ice, creating a visible atmosphere. Just like comets we've observed thousands of times in our own solar system. Everything screamed normal comet, which is strange. Here's why. Different stellar systems form under different conditions. They condense from clouds of dust and gas with varying compositions. The proportions of different elements, carbon, nitrogen, oxygen, silicon, metals, depend on the particular region of the galaxy, the specific supernovae that seeded that region with heavy elements, the timing of star formation. Each stellar system should have a unique chemical signature, subtle differences in composition that reflect its formation history. 3I/ATLAS came from another star system. It formed somewhere else, under different conditions, from different raw materials. We should expect it to look exotic, foreign, chemically distinct from solar system objects. There should be unusual isotope ratios, unexpected element abundances, something that marks it as alien. Instead, it looked familiar. The composition matched solar system comets almost perfectly. The behavior, the way the ice sublimated, the structure of the coma, the development of a faint tail, all completely ordinary. If you showed a spectroscopist data from 3I/ATLAS without telling them where it came from, they'd identify it as a standard comet from our own Oort cloud without hesitation. Too familiar, perhaps. Too perfectly normal. If you wanted to design a probe to study a developing civilization without alarming them, how would you do it? You'd make it look natural. You'd encase your technology in materials that match what they're familiar with. You'd use ice, the most common solid material in space. You'd include typical molecules that would sublime naturally when heated. You'd follow a ballistic trajectory that requires no obvious propulsion. You'd make detection require genuine technological achievement. The kind of sophisticated survey systems we only recently developed But once detected, you'd look reassuringly ordinary. You'd hide in plain sight. I'm not saying that's what 3I/Atlas was. The natural explanation remains far more likely. But the thought experiment is worth considering, because it highlights how unsettling too normal can be when you're expecting exotic. The brightness variations added another layer of data. As 3I/Atlas traveled, its brightness changed periodically. This happens because the nucleus, the solid core beneath the coma, was tumbling, rotating as it moved. Different surfaces reflect different amounts of sunlight. As the object rotates, we see brighter and darker regions alternately, creating a periodic variation in total brightness. Analysis of these brightness changes indicated a rotation period somewhere between 7 and 9 hours. Not particularly fast, not particularly slow. Again, completely ordinary for a cometary nucleus. The size estimates came from multiple methods: brightness measurements, coma extent, and mass estimates from non-gravitational forces. The consensus settled on approximately 960 meters in diameter. Picture 3 football fields laid end to end that's roughly the size of this object's solid nucleus. Substantial, but not enormous. Large enough to be detected at the distances we observed it. Small enough to have been plausibly ejected from another star system by gravitational interactions with giant planets during that system's formation. Again, the size fits perfectly within theoretical predictions for interstellar objects. Nothing unusual, nothing unexpected. Which brings us back to the central discomfort that keeps nagging at anyone who studies this data carefully. Everything fits. Every measurement, every observation, every characteristic falls within the range expected for a natural comet ejected from another stellar system and drifting through the galaxy for millions of years before happening to pass through our neighborhood. The mathematics work. The physics works. The chemistry works. There's no anomaly we can definitively point to and say, that doesn't fit natural explanation, except the frequency, except the timing, except the trajectory patterns, except the statistical improbability that we develop detection capability and immediately start finding these objects at rates far higher than predicted. The mathematics tell us 3I/Atlas came from another star. That much is certain: the eccentricity of 3.3 can't be explained any other way. The observations tell us it looks like a natural comet in every measurable way. That's the most straightforward interpretation of the spectroscopic and photometric data. But the statistics whisper that something unusual is happening. The models predicted we'd wait decades between detections. We waited 25 months. The models predicted random trajectory distributions. We've seen clustering. The models predicted we might never detect any interstellar objects until our technology improved substantially. We detected 2 almost immediately after deploying new survey systems. When mathematics, observations, and statistics don't align comfortably when the pieces fit individually, but the overall picture feels wrong, that's when science gets interesting. That's when we start asking harder questions. That's when hypotheses that seemed absurd begin to feel worth investigating. The numbers tell us something. They tell us this object is extraordinary simply by existing an interstellar visitor, only the second we've ever definitively identified. Proof that material flows between stellar systems and occasionally passes through ours. But they also tell us something more subtle. They tell us the universe might not be working quite the way our models predicted. They tell us there's something we don't understand yet either, about natural processes, or about the possibility that these objects might not be entirely natural. The mathematics of 3I/Atlas are impossible to ignore. An eccentricity of 3.3 means it came from another star, no question. But what that really means, whether it's a natural wanderer or something more purposeful, that's the question that keeps astronomers up at night. And the answer, whatever it turns out to be, will change how we see the universe forever. For most of human history, suggesting that objects in the sky might be artificial, that they might be spacecraft or probes from other civilizations, was a fast path to professional suicide. You didn't make those suggestions if you wanted to be taken seriously. You didn't propose alien origins for astronomical phenomena if you valued your reputation. The assumption was ironclad. Everything up there is natural. The planets moved predictably, following Kepler's laws with mathematical precision, obviously not under intelligent control. Comets appeared on schedules, their orbits determined by gravity and nothing else, nature, not intention. Even when telescopes revealed the true nature of celestial objects, that Mars had polar caps, that Jupiter had storms, that Saturn had rings, the assumption remained firm. Natural processes explained everything. No intelligence required. This assumption held for good reason. Every time someone suggested artificial origins for an astronomical phenomenon, natural explanations eventually emerged. The track record was perfect. Natural processes always won. The most famous example happened in 1967. A graduate student named Jocelyn Bell, working at Cambridge University, was analyzing data from a new radio telescope. She noticed something extraordinary: radio signals pulsing with unbelievable precision. The pulses arrived exactly 1.337 seconds apart. Then again, and again. The timing was so regular, so precise, that it seemed impossible for any natural process to produce it. The team working on the project was genuinely uncertain. They briefly called these signals LGM-1, LGM standing for Little Green Men. It wasn't entirely a joke. The precision suggested artificial origin. Perhaps they'd detected a beacon from an alien civilization. Perhaps this was first contact, disguised as a mysterious radio signal. Within months, the mystery was solved. Natural explanation emerged, and it was extraordinary in its own right. The signals came from a rapidly rotating neutron star, the collapsed core of a massive star that had exploded as a supernova. This neutron star, just 20 kilometers across but containing more mass than our Sun, was spinning 30 times per second. Beams of radio waves, generated by the star's intense magnetic field, swept past Earth like a lighthouse beam. Each time the beam pointed toward us, our telescopes detected a pulse. We call them pulsars now. We've detected thousands of them. They're completely natural, completely explainable by physics we understand. The precision that seemed to demand intelligence was actually just the precision of physics, a massive object spinning in space, conserving angular momentum, as regular as clockwork, because the laws of nature are regular as clockwork, natural, not artificial. The pattern held. But something shifted in the late 20th and early 21st centuries. Something that fundamentally changed how we think about the possibility of artificial objects in space. The shift began with exoplanets. For thousands of years, humans assumed planets were rare. We knew about the planets in our solar system: Mercury through Saturn, visible to the naked eye, Uranus and Neptune discovered through telescopes. But other stars having planets? That was speculation. We had no evidence. Many scientists suspected other stars might have planetary systems, but we couldn't prove it. We couldn't detect them. The first confirmed detection of a planet around a Sun-like star came in 1995. Astronomers Michel Mayor and Didier Queloz, working at the University of Geneva, detected a planet orbiting the star 51 Pegasi. The planet was massive, about half the mass of Jupiter, and orbiting incredibly close to its star, completing one orbit every 4 days. It was nothing like the planets in our solar system, which made the discovery even more remarkable. Planets, apparently, could form in configurations we'd never imagined. Then the floodgates opened. Better detection techniques revealed more planets. Then more. Then hundreds. Then thousands. The Kepler Space Telescope, launched in 2009 and operating until 2018, revolutionized the field. It stared at one patch of sky continuously, watching over 150,000 stars, looking for the tiny dip in brightness that occurs when a planet passes in front of its star from our perspective. Kepler found thousands of planets. Statistical analysis of Kepler's data revealed something profound. Planets aren't rare, they're everywhere. Current estimates suggest there are hundreds of billions of planets in our galaxy alone. Not millions, not billions, hundreds of billions. Nearly every star has at least one planet. Many have multiple planets. Planetary systems are the rule, not the exception. And many of these planets orbit in the habitable zone, the region around a star where temperatures allow liquid water to exist on a planet's surface. Potentially billions of worlds in our galaxy alone could harbor life. Think about what this does to the equation. If planets are common, and we know they are, and if habitable planets are common, and evidence suggests they are, then maybe life is common. We don't know that yet. We have only one confirmed example of life, Earth. But the ingredients are there. The opportunities are there. The universe has had billions of years to work with, and if life is common, perhaps intelligence isn't impossibly rare. Perhaps technological civilizations aren't unique anomalies. Perhaps we should actually expect to find evidence of other civilizations, rather than assuming we're alone. This shifting perspective, this realization that the universe is far more hospitable to life than we previously imagined, created space for previously unthinkable discussions in astronomy. The Overton window shifted. Questions that would have been dismissed as unscientific in 1990 became legitimate areas of inquiry by 2015. When Oumuamua arrived in October 2017, most astronomers assumed natural origin. It was weird. Certainly its elongated shape, its tumbling motion, the reddish color suggesting radiation exposure over millions of years. But weird doesn't mean artificial. The universe produces plenty of weird through entirely natural processes. Then observations revealed something genuinely puzzling. Oumuamua was accelerating, not by much tiny deviations from the purely gravitational trajectory, but measurably. Something was providing thrust, pushing the object faster than gravity and solar radiation pressure alone could account for. For a comet, this would be normal. Cometary outgassing ice sublimating from the surface as the object heats up, creating jets that act like tiny rocket engines, easily explains small accelerations. We've observed this countless times with solar system comets, but Oumuamua showed no signs of outgassing, no coma, no tail, no spectroscopic signatures of sublimating ice. Just acceleration with no visible mechanism. The mystery deepened. Explanations were proposed. Maybe it was outgassing, but the jets were composed of materials that don't show visible signatures. Pure hydrogen, perhaps, which would sublime without leaving detectable traces. Maybe the object was unusually shaped in ways that made solar radiation pressure more effective than normal calculations suggested. Maybe it was tumbling in specific ways that concentrated thrust. All plausible, all possible, but none entirely satisfying. Then Avi Loeb, chair of Harvard University's astronomy department, published a paper that broke the unwritten rule. In late 2018, Loeb and his colleague Shmuel Bialy suggested we shouldn't automatically rule out artificial origin. Perhaps Oumuamua was a light sail, a thin, reflective surface pushed by starlight, technology we ourselves are currently developing for interstellar travel. A light sail would show exactly the kind of acceleration Oumuamua displayed, thrust without visible exhaust, proportional to solar radiation intensity, no chemical signatures. The response from the astronomical community was swift and often harsh. You don't suggest alien technology without extraordinary evidence. Carl Sagan's famous principle, extraordinary claims require extraordinary evidence, was invoked repeatedly. Loeb was accused of seeking publicity, of abandoning scientific rigor, of promoting speculation over data-driven analysis. But Loeb persisted. His argument was straightforward. Science should follow evidence wherever it leads. We shouldn't rule out hypotheses simply because they're uncomfortable or socially unacceptable. If the data suggests artificial origin might explain observations better than natural processes, we should investigate that possibility seriously, not dismiss it reflexively. He wrote a book published in 2021, Extraterrestrial: The First Sign of Intelligent Life Beyond Earth. The controversy intensified. Some colleagues distanced themselves. Others privately admitted they found his arguments intriguing, even if they wouldn't publicly support them. The debate created ripples throughout astronomy, forcing uncomfortable conversations about bias, about the boundaries of acceptable inquiry, about whether the field was too quick to dismiss certain possibilities. Then came 3I/Atlas in August 2019, arriving while the Oumuamua controversy still raged. This one was different. Unlike Oumuamua, 3I/Atlas looked conventionally cometary from the start. It had a coma. It developed a faint tail as it approached the sunday. Spectroscopy showed standard comet composition, water ice, cyanogen, carbon compounds. Its behavior was completely ordinary, completely explainable through natural processes. Case closed, right? Natural comet from another star system. Exactly as initial predictions suggested interstellar objects should appear. Nothing to see here. No need for exotic explanations. Except for that timing issue that wouldn't go away. 2 interstellar objects in 3 years. The updated probability calculations started circulating through astronomical circles, passed through email chains, discussed at conferences. One team published revised estimates in peer-reviewed journals, trying to reconcile observations with models. Their conclusion: based on these 2 detections, we should now expect between 0.2 and 20 interstellar objects per year, depending on model assumptions. 0.2 to 20. That's a range spanning 2 orders of magnitude, 100-fold uncertainty. It indicates profound disagreement about the true population density. Some models suggest 1 detection every 5 years. Others suggest multiple detections every year. Both can claim to fit the data, because we have so little data. But even the high end of these estimates created discomfort. We just happen to develop detection capability sophisticated, automated survey systems like Atlas and Pan-STARRS that scan the entire sky repeatedly, right when interstellar objects started showing up at detectable rates. The coincidence felt orchestrated. The test hypothesis evolved from this discomfort. It went through several iterations, each more sophisticated than the last, as people thought, through the implications more carefully. Early versions were simple. Advanced civilizations send probes to study developing species. They watch. They monitor. They report back. These probes drift through the galaxy, visiting stellar systems, gathering data about whatever civilizations might be emerging. We're being watched, perhaps, studied, catalogued. But this version raised immediate questions. Why use physical probes? Why not just observe electromagnetically from a distance? We can detect radio emissions from thousands of light years away. A sufficiently advanced civilization could probably monitor us through passive observation without ever entering our solar system. Why risk detection by sending physical objects? The hypothesis refined. Perhaps these aren't just monitors. Perhaps they're calibration tests. An advanced civilization managing some kind of galactic network needs to know which stellar systems contain technological species. More specifically, they need to know what those species are capable of detecting. What's their technological threshold? Can they distinguish interstellar objects from local solar system members? How quickly do they respond to unusual observations? What's their level of astronomical sophistication? You don't measure those capabilities by asking. You measure by sending something and watching the response. Send an object through a stellar system. If the local civilization detects it and correctly identifies it as interstellar, they've reached a significant technological milestone. They have sophisticated enough instruments and analysis capabilities to recognize visitors from other star systems. They're ready for the next level of contact, whatever that might be. If they don't detect it, if it passes through unnoticed, they're not ready yet. Their technology isn't sufficient. Check back in a few hundred years. This version of the hypothesis gained surprising traction, even among conservative astronomers who would never publicly endorse it. The logic is sound. If you're managing a galactic civilization or communication network, if you're part of some larger structure spanning multiple star systems, you need information about your neighbors. You need to know who's out there, what they're capable of, whether they're approaching readiness for contact. Direct contact is risky. You don't know how they'll respond. History shows that encounters between civilizations at different technological levels often go poorly for the less advanced civilization. Maybe advanced species learn to be cautious. Maybe there are protocols established over millions of years about how to approach emerging civilizations without causing harm. But sending a probe disguised as a natural object, that's safe. That's informative. That's non-threatening. If they detect it and identify it as interstellar, you've learned something crucial about their capabilities. If they don't detect it, you've also learned something. Either way, you've gathered data without revealing yourself, without risking harmful contact. The hypothesis evolved further to address specific observations. Why does 3I/Atlas look so conventionally cometary? Why does it match solar system comet composition so perfectly? Because disguise is the point. A civilization capable of interstellar travel, capable of sending probes between star systems, could certainly design those probes to mimic natural objects. The engineering is straightforward, at least in principle. Encase your technology in volatile ices. Use water ice, the most common solid material in the universe. Include simple molecules like cyanogen and carbon compounds. Make the outer layers identical to natural comet composition. As the probe approaches the target star, solar heating sublimates the outer layers naturally, creating a convincing cometary appearance. Coma forms, tail develops, everything looks exactly as the target civilization expects a comet to look. Meanwhile, the actual instrumentation, the sensors, the data storage, the power systems, whatever technology the probe contains, remains hidden beneath those sublimating layers, protected, disguised. Invisible to the primitive sensors of the civilization being studied, follow a ballistic trajectory through the system. No obvious propulsion once you're within detection range. Let gravity determine your path. Make detection require genuine technological achievement, the kind of sophisticated, automated survey systems that only emerge when a civilization reaches a certain threshold. If they spot you, they've proven they're capable. If they don't, they're not ready yet. The objections to this hypothesis are substantial, and any honest discussion has to acknowledge them. First, it violates Occam's razor, the principle that simpler explanations are generally preferable to complex ones. Natural explanation suffices. We don't need to invoke intelligence where natural processes explain observations adequately. Second, it requires stacking multiple unproven assumptions. Advanced civilizations exist. They care about monitoring emerging species. They use these particular methods. They happen to be watching our stellar system right now. Each assumption individually might be plausible, but multiplying them together reduces overall probability substantially. Third, the statistical argument about detection frequency cuts both ways. Maybe our models of interstellar object populations were simply wrong. Maybe these objects are naturally common, and we're only now developing the technology to detect them regularly. The timing isn't suspicious, It's just the inevitable result of improving technology, eventually becoming sensitive enough to detect a phenomenon that was always there. These are valid objections. Science demands we maintain them. We can't abandon skepticism just because a hypothesis is intriguing. But here's what shifts this discussion from fringe speculation to legitimate scientific inquiry. The test hypothesis makes testable predictions. If these are tests, if they're probes sent by advanced civilizations to measure our detection capabilities, then we should see certain patterns in future observations. We should detect more interstellar objects in coming years, perhaps with increasing frequency as our detection capability improves. Because if someone's testing us, they want to see how we respond as our technology develops. We should see trajectory preferences. Random natural objects should arrive from uniformly distributed directions. But if these are tests, they might preferentially approach through the ecliptic plane, where detection from Earth is most likely. They might target trajectories that maximize observability. We might eventually detect one with clearer artificial signatures, anomalous acceleration that can't be explained by outgassing, unusual composition that doesn't match natural formation, electromagnetic emissions at specific frequencies, surface features too geometric to be natural, something definitive. And crucially, we should see these detections cluster around Earth's location rather than being uniformly distributed through space. If you're testing us specifically, you send them where we can detect them. You don't send them randomly through regions of the solar system we can't observe. These predictions are falsifiable. We can test them. As more interstellar objects are detected and the Vera Rubin Observatory coming online will detect many more, and we'll accumulate statistical data. We'll see whether trajectories are random or clustered. We'll see whether detection rates remain constant or increase. We'll see whether composition is diverse or suspiciously uniform. The hypothesis can be proven wrong. That's what makes it scientific rather than pseudo-scientific speculation. The truly remarkable shift in astronomy over the past decade isn't that some scientists are proposing the test, hypothesis. It's that major astronomical institutions are taking the possibility seriously enough to design detection and analysis protocols, not because they believe it. Most astronomers remain deeply skeptical, but because the cost of missing genuine evidence of extraterrestrial technology would be catastrophic to science. Better to investigate and rule out than dismiss and miss. The SETI Institute, the organization dedicated to searching for extraterrestrial intelligence, has expanded its focus to include looking for physical artifacts, not just radio signals. NASA has funded studies on how to detect technosignatures, signs of technology, in astronomical observations. The European Space Agency is designing missions that could intercept and study interstellar objects up close. This isn't because everyone believes we're being visited by alien probes. It's because the question has moved from obviously absurd to worth investigating seriously. The test hypothesis, born from statistical anomalies and timing coincidences, has evolved from fringe speculation to legitimate scientific question. That evolution itself tells a profound story about how science adapts when faced with data that doesn't quite fit comfortable patterns. 50 years ago, suggesting Oumuamua might be artificial would have ended careers. Today, Avi Loeb remains a respected figure in astronomy, even among those who disagree with his conclusions. The conversation has changed. The boundaries of acceptable inquiry have expanded. We still don't know what 3I/Atlas truly was. Natural explanation remains far more likely than artificial. But the question, could it have been a test, is no longer automatically dismissed. It's investigated, it's analyzed, it's incorporated into planning for future observations. And that represents a fundamental shift in how we think about our place in the universe. We're not just passive observers anymore. We're actively considering the possibility that we might be observed in return, that the universe might contain other intelligences, that some of those intelligences might have technology advanced enough to send probes between stars. Whether 3I/Atlas was such a probe remains unknown, but the fact that we're asking the question seriously, rigorously, with proper scientific methodology represents a threshold crossed. We're ready to consider possibilities that previous generations would have dismissed without examination. We're prepared to investigate, to test, to gather evidence. And if the answer turns out to be yes, if we eventually confirm that some of these interstellar visitors are artificial, we'll look back at 3I/Atlas as the object that made us start asking the right questions. The evolution of this idea, from unthinkable to testable, is itself one of the most fascinating parts of this story. September through December of 2019 represents one of the most intensive astronomical observation campaigns in recent history. The target wasn't a supernova or a colliding galaxy or any of the usual spectacular events that capture telescope time. It was a faint, fuzzy dot moving against the background stars, getting fainter every single day as it raced away from the inner solar system at 33 kilometers per second. The urgency was absolute. Unlike planets that orbit predictably for millennia, unlike asteroids that we can observe again next year or next decade, unlike comets that return on schedules we can calculate centuries in advance, this visitor would pass through exactly once. One opportunity, one brief window. Miss it, and the chance vanishes forever. Picture the coordination this required. Professional observatories don't operate casually. Telescope time is precious, rationed like gold. Observing schedules are planned months or even years in advance through competitive proposal processes. Astronomers submit detailed applications, explaining what they want to observe and why. Panels of experts review these proposals, ranking them, selecting the most scientifically valuable. Time allocation committees make final decisions. Every hour of telescope time on major instruments is spoken for, scheduled, and committed. Then suddenly an interstellar object appears, and all those careful plans become negotiable. The Gemini North Telescope in Hawaii, an 8.1-meter mirror sitting atop Mauna Kea, one of the world's premier observing sites, reorients to capture spectra of 3I/Atlas. Scheduled observations get bumped. Other astronomers, who'd waited months for their allocated time, graciously step aside. The science case is irresistible. An interstellar visitor, only the second ever detected, fleeting and irreplaceable. The Very Large Telescope in Chile, actually 4 separate 8.2-meter telescopes that can work independently or combine as an interferometer, dedicates multiple nights to studying this unexpected visitor. Teams coordinate observations to maximize coverage. When the object is visible from Chile, VLT captures data. When Earth's rotation carries it out of view, other telescopes take over. The Hubble Space Telescope, arguably humanity's most valuable astronomical instrument, interrupts its meticulously planned schedule for multiple observation runs. Hubble's advantage isn't size. Ground-based telescopes are much larger, but clarity. Orbiting above Earth's atmosphere, Hubble sees without the blurring effects of atmospheric turbulence. Its images are pristine, limited only by the laws of optics, not by weather or air currents. Smaller observatories worldwide contribute what they can: position measurements to refine trajectory calculations, brightness monitoring to track variations, photometry to determine color. Every data point matters. Every observation adds to the collective understanding. The data accumulates day by day, night by night. Spectroscopy reveals composition, splitting the faint reflected sunlight into component wavelengths. The spectrum shows emission lines, bright bands at specific wavelengths, where gases in the object's coma are absorbing and re-emitting light. Cyanogen gas produces characteristic emission at certain wavelengths, diatomic carbon at others. Water ice sublimates, creating hydroxyl molecules that produce their own spectral signatures. Each emission line tells a story about chemistry, about what this object is made of, about processes occurring on and around its surface. Photometry tracks how brightness changes over time. The object gets fainter as it moves farther from both the Sun and Earth that's expected, just geometry and the inverse square law of light. But there are also periodic variations. The brightness fluctuates on a timescale of several hours. This indicates rotation. As the nucleus tumbles, different surface areas face us, each reflecting different amounts of sunlight. Darker regions make the object appear dimmer. Brighter regions increase total light output. By analyzing these variations carefully, their amplitude, their periodicity, their detailed structure, astronomers can estimate rotation period and infer shape. The data suggests 3I/Atlas was spinning with a period somewhere between 7 and 9 hours. Not particularly fast, not unusual, completely ordinary for a cometary nucleus. Astrometry precise position measurements becomes crucial for refining trajectory calculations. Early observations pin down the object's location to within certain uncertainty boundaries. Each additional position measurement narrows those boundaries. The orbital parameters become more precise. The eccentricity calculation, initially uncertain to several decimal places, solidifies. 3.3. Confirmed and reconfirmed. The origin direction in interstellar space becomes clearer. We can't identify a specific star it came from. The uncertainties are too large for that, and the object has been traveling for so long that stellar motions have shifted everything. But we can identify the general region of sky it originated from before entering our solar system. By November, consensus emerges among the astronomical community. Definitely interstellar, the mathematics are unambiguous. Definitely active, showing genuine cometary behavior with outgassing and coma formation. Definitely similar to solar system comets in composition and physical characteristics. The papers are already being written. The data is being analyzed, formatted, prepared for peer review. But here's what haunts the astronomers involved in this campaign. Here's what keeps them up at night even now, years later. What didn't they measure? What couldn't they measure? What opportunities slipped away because the technology wasn't quite good enough, because the timing wasn't quite right, because the object was already too far away when they realized what questions to ask? High-resolution imaging, for instance. Even Hubble, with its exquisite optics and position above the atmosphere, can't resolve surface details on an object 960 meters across located billions of kilometers away. The laws of physics, specifically the diffraction limit determined by telescope aperture and observation wavelength, impose fundamental constraints. You can't see details smaller than a certain angular size, no matter how perfect your telescope. The best images of 3I/Atlas show a blur, an elongated, fuzzy shape, definitely a coma surrounding a nucleus, but no surface features, no structure, no details that would tell us anything about the actual solid body beneath the gas cloud. If there were geometric patterns on the surface, straight edges, right angles, repeated structures that might indicate artificial origin, the resolution wasn't sufficient to detect them. If there were solar panels or antenna arrays or any obviously technological features, they remained invisible, hidden beneath the limits of what optics could resolve at that distance. Radio telescopes listened for signals. Several facilities pointed their dishes at 3I/Atlas, scanning for any electromagnetic emissions that might indicate active technology. They found nothing, but they could only monitor narrow frequency ranges. The radio spectrum is vast. They couldn't listen to every possible frequency simultaneously, continuously, throughout the entire observation window. If the object was transmitting at frequencies or times they weren't monitoring, those signals went undetected. Infrared telescopes checked for excess heat signatures. An active probe with internal power sources would generate waste heat. That heat would radiate at infrared wavelengths, potentially detectable by thermal imaging. The observations showed nothing unusual, just the temperature you'd expect from solar heating of ice and rock at that distance from the Sunday. But the sensitivity had limits. Subtle emissions could easily hide beneath the detection threshold. A well-designed probe with efficient heat management could potentially mask its thermal signature, making it indistinguishable from a natural object's temperature profile. The rotation period estimate of 7 to 9 hours comes from brightness variations. But what if the object wasn't simply tumbling? What if it was rotating in a controlled manner? Or what if the brightness changes indicated something else entirely? Venting from specific locations, perhaps, or reflections from surfaces that weren't randomly distributed. The data allows multiple interpretations. Without higher resolution imaging, without close-up observations, distinguishing between these possibilities becomes impossible. The cyanogen emission shows peaks and variations throughout the observation period. The conventional interpretation: uneven distribution of ice on the surface. Some regions are richer in cyanogen-bearing compounds. As these regions rotate into sunlight, sublimation increases and emission peaks. Completely normal for a comet. But what if those variations indicate controlled outgassing? What if a probe were managing its thermal profile or adjusting its orientation using carefully timed gas releases? Would we be able to distinguish that from natural processes with the data we collected? Probably not. The signatures would be too subtle, too easily explained by irregular surface composition. The light curve, the detailed record of how brightness changed over time, shows minor unpredictabilities, small deviations from smooth, periodic variation. These are attributed to irregular shape. Cometary nuclei aren't spheres. They're lumpy, potato-shaped objects with irregular surfaces. That irregularity creates complex brightness variations as they rotate. But could those deviations indicate active systems adjusting orientation? Course corrections too small to measure directly but large enough to affect rotation. Again, with the limited data available, distinguishing between these scenarios is impossible. The trajectory itself tells a frustrating story of missed opportunities. 3. I/Atlas. Approach the Sun from above the ecliptic plane, the flat disk where planets orbit. It crossed down through the plane, swung through perihelion on December 8th at approximately 2 astronomical units, then departed below the plane. The geometry meant Earth-based observers had only certain viewing angles at certain times. When the object was above the plane, Southern Hemisphere telescopes had better views. After perihelion, Northern Hemisphere facilities gained advantage. But there were periods, days at a time, when the object's position in the sky made observations difficult or impossible from major observatories. Weather added another constraint. Clouds don't care about interstellar visitors. Mauna Kea, typically one of the clearest observing sites on Earth, experienced cloudy nights during critical observation windows. Observatories in Chile faced similar issues. Time was lost. Data wasn't collected. Opportunities slipped away. The optimal observation window lasted roughly 3 months, from discovery in early September through early December. During this time, the object was bright enough for detailed study with major telescopes. It was positioned favorably for observations from Earth's major observatories. The geometry worked, but even that window was closing fast. Every day, the object moved farther from both the Sun and Earth. Every day, it became fainter, more difficult to observe, harder to study. By mid-January 2020, only the very largest telescopes could still detect it. The signal was becoming too weak for spectroscopy. Detailed brightness measurements became impossible. Even basic position measurements required long exposures on premier instruments. By February, it was gone, lost in the vast darkness of space, racing away at 33 kilometers per second relative to our Sunday, moving faster than anything bound to the solar system. Every second, it traveled 33 kilometers farther away. Every hour, nearly 120,000 kilometers. Every day, almost 3 million kilometers more distant. In a year, it would be farther from the Sun than Pluto. In a decade, beyond the Kuiper Belt, that ring of icy bodies marking the outer boundary of the planetary region. In a century, back in interstellar space where it came from, indistinguishable from the cosmic background of wandering objects. Gone, unrecoverable, beyond our reach forever. What could we have learned with better preparation? This question torments the scientists who observed 3I/Atlas. Not because they did anything wrong, they responded as quickly as possible with the tools available, but because they know how much more they could have discovered with advanced preparation. Mission concepts were frantically drafted during the observation window. Teams of engineers and scientists working on compressed schedules, proposed spacecraft that could launch and intercept the object, examine it up close, perhaps even land on its surface or collect samples. The concepts were technically feasible. Chemical propulsion could achieve the necessary velocities. Gravitational assists from Jupiter could boost speed further. A spacecraft launched within weeks of discovery, on an optimal trajectory, could potentially have caught up with 3I/Atlas during its outbound journey. But spacecraft aren't assembled in weeks. They take years to build, years to test, years to plan, to design, to construct, to validate. The fastest spacecraft ever launched, New Horizons to Pluto, required years of development even after its mission was approved and funded. 3I/Atlas would be long gone before any hastily conceived mission could launch. The opportunity existed only on paper, in proposal documents, in mission concepts that will never fly. The frustration is palpable in the scientific literature. You can read it between the lines of papers published about 3I/Atlas, professional measured language constrained by peer review requirements. But underneath, a shared sense of missed opportunity. We had something precious, an interstellar visitor, willing to be studied, passing through our neighborhood, and we lacked the infrastructure to fully exploit it. We could observe remotely. We did observe remotely, extensively, with the best ground-based and space-based telescopes available. We collected valuable data. We learned important things. But we couldn't examine directly. We couldn't touch, we couldn't sample, we couldn't measure with instruments placed directly on or near the object. All our data came from light-reflected sunlight, thermal radiation, spectroscopic emissions analyzed from billions of kilometers away. It's the difference between examining a photograph of an object and holding that object in your hands. Both provide information, but one provides so much more. This frustration drives current policy changes in space agencies worldwide. Multiple organizations now have rapid response mission concepts in various stages of development. Not missions designed for specific targets, but missions designed to wait and watch, ready to deploy on short notice when a promising target appears. The European Space Agency's Comet Interceptor mission represents the most advanced of these concepts. Currently scheduled for launch in 2029 aboard an Ariane 6 rocket, this mission won't target a known object. Instead, it will position itself at the L2 Lagrange point, a gravitationally stable location approximately 1.5 million kilometers from Earth, on the side away from the Sunday. There, it will wait. Systems dormant to conserve fuel and extend operational lifetime, but monitoring, watching, ready. When a promising target appears, a long-period comet making its first passage through the inner solar system, or ideally, an interstellar object, the mission activates. Calculations begin immediately. Trajectory options are evaluated. The European Space Agency convenes decision panels. Can we intercept this target? Do we have enough fuel? Is the science case compelling enough to commit? If the decision is go, Comet Interceptor separates into 3 components: a main probe and 2 smaller subprobes. They target different intercept trajectories, approaching the object from different angles to maximize coverage and redundancy. If one probe fails or can't achieve optimal positioning, the others continue. The mission carries a suite of instruments specifically designed for close-up study of comets and potentially interstellar objects. Cameras for high-resolution imaging, spectrometers for composition analysis, magnetometers for measuring magnetic fields, dust analyzers for examining particles ejected from the surface, plasma sensors for studying the interaction between the object and the solar wind. Everything designed for rapid deployment, quick intercept, maximum science return from a fleeting encounter. But Comet Interceptor won't launch until 2029 at the earliest. That's a decade after 3I/Atlas. Every interstellar object detected before that launch will face the same constraint we faced with 3I/Atlas: observation from a distance, no direct examination, limited data, frustrating gaps. The scientific papers published from the 3I/Atlas observation campaign tell the official story. Peer-reviewed publications in prestigious journals, composition data, trajectory analysis, physical characteristics, comparisons to solar system comets. Conclusions stated carefully, measured, supported by data. The papers are models of scientific rigor. They acknowledge uncertainties. They present alternative interpretations. They avoid speculation beyond what data supports. But talk to the astronomers privately. Listen to presentations at conferences where the audience consists entirely of colleagues who understand the context. Read between the lines of careful phrasing. A different tone emerges. Not certainty that something artificial visited us, but discomfort with how perfectly normal everything appeared, puzzlement about the timing, awareness that current explanations, while adequate, aren't entirely satisfying. One researcher, speaking at a planetary defense conference, a forum where scientists discuss how to detect and potentially deflect asteroids that might threaten Earth, put it more bluntly than published papers could. The quote didn't make it into peer-reviewed literature, but it captures a sentiment shared more widely than official channels acknowledge. The problem with 3I/Borisov is that it's too good an interstellar comet. It's exactly what we would design if we wanted to send a probe that looked natural. Too good, too perfect, too normal. When the expected becomes suspicious, when just right feels wrong, you're deep into uncomfortable territory where data and intuition conflict. The official conclusion stands. 3I/Atlas was a natural comet from another star system, similar in composition and behavior to solar system comets, following a ballistic trajectory determined by its entry velocity and the Sun's gravitational field. Nothing in the data definitively contradicts that conclusion, but nothing definitively proves it either. The gaps in our observations, the limits of our instruments, the brevity of the observation window, all these conspire to leave questions unanswered. Could high-resolution imaging have revealed artificial structures? We'll never know. We didn't have sufficient resolution. Could continuous radio monitoring have detected signals? We'll never know. We didn't monitor continuously across all frequencies. Could close-up examination have found isotope ratios inconsistent with natural formation? We'll never know. We didn't examine it up close. Could landing on the surface have discovered materials or structures that proved artificial origin? We'll never know. We didn't land on it. 3I/Atlas passed through our solar system carrying secrets we couldn't unlock, not because we weren't trying, not because we weren't interested, but because we weren't ready. We had the technology to detect it. That threshold we'd crossed. We could spot interstellar visitors, calculate their trajectories, confirm their extrasolar origin, but the technology to study them thoroughly, to answer the deeper questions, to determine not just where they came from, but what they truly are. That technology we're still developing. Those capabilities we're still building. Those missions we're still planning. Next time, we'll be more ready. Not completely ready, that might take decades more, but more ready than we were for 3I/Atlas. And there will be a next time. The statistics now suggest we'll detect more interstellar objects within years, not decades. The Vera Rubin observatory coming online will revolutionize detection. More visitors are coming. When they arrive, we'll have learned from this experience. We'll have better instruments, better protocols, better preparedness. But 3I/Atlas, the second interstellar object ever detected, the mysterious visitor that looked too perfectly normal, will remain forever partially unknown. A mystery we glimpsed but couldn't fully solve. An opportunity we recognized but couldn't fully seize. The data we collected is valuable. The lessons we learned are crucial. But the questions we couldn't answer will haunt astronomy for decades. What was it really? We'll never know for certain. And that uncertainty, that gap in knowledge, that missed opportunity, that's the price we paid for being the generation that first detected these visitors but didn't yet have the tools to truly understand them. Next time, we'll be different. Next time, we'll be ready. But we'll never get another chance with 3I/Atlas. That opportunity has passed, racing away at 33 kilometers per second into the darkness between stars, carrying its secrets with it forever. If we're going to entertain the test hypothesis seriously, not as proven, but as worth investigating, we need to move beyond vague speculation. We need to understand exactly how such a thing could work. Not hand-waving about advanced technology we can't imagine. Not appeals to physics we don't understand, but actual engineering grounded in principles we know are real. Because if the underlying principles are impossible, if they violate fundamental laws of physics, then the hypothesis fails completely. It becomes science fiction, not science. But if the principles are merely difficult, if they require technology we don't yet possess but could develop, then the hypothesis remains viable. It becomes engineering, not impossibility. And examining these mechanics reveals something surprising. Nothing about the test hypothesis requires physics beyond what we currently understand. It requires engineering beyond our current capability, yes, but not impossible engineering, just advanced engineering. Let's start with the fundamental challenge: interstellar travel itself. The distances between stars are almost incomprehensibly vast. Our nearest stellar neighbor, Proxima Centauri, lies 4.2 light-years away. Light, traveling at 300,000 kilometers per second, the fastest speed possible in our universe, takes 4.2 years to cover that distance. At 33 kilometers per second, 3I/Atlas's velocity through our solar system, the journey from Proxima Centauri would take approximately 40,000 years. Not 4 years, not 40 years. 40,000 years. Chemical rockets can't do better. Even nuclear rockets, using nuclear reactions instead of chemical combustion for propulsion, can't achieve dramatically higher velocities within reasonable mass budgets. The tyranny of the rocket equation limits what's possible. To go faster, you need more fuel, but more fuel means more mass, which requires even more fuel to accelerate. The problem compounds exponentially. For true interstellar travel at reasonable timescales, you need fundamentally different approaches. Several are theoretically sound, requiring no new physics, just engineering we haven't yet mastered. Light sails represent the most plausible near-term option. The concept is beautifully simple: a large, thin, highly reflective surface pushed by light pressure. Photons, particles of light, carry momentum. When they reflect off a surface, they transfer that momentum, creating thrust. The effect is tiny for small surfaces, but a sufficiently large sail pushed by sufficiently intense light can achieve impressive accelerations. Solar sails work this way, using sunlight for propulsion. We've already tested this technology in space with missions like IKAROS, launched by Japan in 2010, and LightSail 2, launched by the Planetary Society in 2019. These demonstrations proved the concept works. But for interstellar travel, you need something more powerful than sunlight alone. You need a laser, a powerful focused beam of light, capable of pushing a sail to significant fractions of light speed. The Breakthrough Starshot initiative, funded by billionaire Yuri Milner and endorsed by the late Stephen Hawking, aims to develop exactly this technology. The concept: build a massive ground-based laser array capable of generating gigawatts of power. Launch thousands of tiny probes, each weighing just grams, essentially a chip with sensors and a large reflective sail. Focus the laser beam on each sail as it climbs out of Earth's atmosphere, pushing it with sustained thrust for minutes or hours. The calculations suggest you could accelerate these tiny probes to 20% of light speed. At that velocity, the journey to Proxima Centauri would take 20 years, not 40,000. Within a human lifetime, we could send probes to another star system. If we can envision building this technology within the next century, and serious engineering studies suggest we can, then a civilization even moderately ahead of us could already possess it. A civilization 1,000 years ahead, they'd have refined it dramatically. 10,000 years ahead, it would be routine. To reach our solar system from typical galactic distances, say 100 light-years away, which encompasses millions of star systems, would take hundreds or thousands of years at these speeds. Long, but not impossibly long. Not millions of years. A civilization could launch probes toward target systems and reasonably expect them to arrive and function. But light sails face a significant problem for covert observation. They're detectable. That large reflective surface catches sunlight brilliantly. It would appear as a bright, obviously artificial object against the dark background of space. If you want stealth, if you want to study a civilization without revealing yourself, you need different approaches. Nuclear pulse propulsion offers one alternative. The concept, studied seriously during Project Orion in the 1950s and 60s, involves detonating small nuclear charges behind a spacecraft, using the explosion's energy for thrust. It sounds insane, but the physics works. You can achieve impressive velocities, potentially 10% of light speed, with fusion-based explosions. The drawback: nuclear explosions leave characteristic radiation signatures, not particularly stealthy. A civilization monitoring space for signs of artificial activity would likely detect those signatures. Ion drives, which we currently use on some space missions, are extremely efficient but provide low thrust. They're excellent for slow, patient missions within a solar system, but less practical for rapid interstellar travel. Fusion rockets remain theoretical for us, but are entirely plausible for advanced civilizations. Controlled fusion forcing hydrogen nuclei to combine into helium, releasing enormous energy in the process, would provide both high thrust and high efficiency. Fusion rockets could potentially achieve 10% of light speed while remaining relatively stealthy, with exhaust signatures that could be minimized or directed away from the target system. The engineering is challenging. We haven't achieved controlled fusion for power generation on Earth yet, much less in a compact rocket engine. But nothing about the physics is impossible. It's engineering difficulty, not physical impossibility. Now consider the disguise problem. You've traveled between stars, a journey taking centuries or millennia. You're approaching a target solar system containing a potentially technological civilization. You want to study them without revealing yourself. You want to measure their detection capabilities, their astronomical sophistication, their response to unusual phenomena. How do you hide your artificial probe in plain sight? You encase it in natural materials. Ice is everywhere in space. Hydrogen and oxygen are the universe's most common reactive elements. Throughout interstellar space, on comets, on moons, in the outer regions of stellar systems, ice is ubiquitous. It's the default building material of the outer solar system and the interstellar medium. A probe traveling between stars could collect ice during its journey. Imagine it equipped with a scoop or net, gathering hydrogen and oxygen from the thin interstellar medium, synthesizing water ice, building up layers on its exterior, or imagine it deliberately passing through the outer regions of stellar systems it encounters, gathering ice from comets or Kuiper belt analogues, accumulating material. By the time it enters the target system, our solar system, it's encased in a thick shell of ice. Irregular shape, naturally occurring composition, appropriate size. From the outside, it's indistinguishable from a natural comet. As it approaches the star, solar heating begins sublimating the outer layers. The ice vaporizes naturally, creating a coma, that fuzzy cloud of gas characteristic of comets. Dust, mixed with the ice, gets released, forming a tail. All the visual signatures of a genuine comet appear automatically, requiring no active systems, no obvious fakery. The ice serves multiple purposes. It's camouflage, making the probe look natural. It's an ablative shield, protecting internal systems from solar radiation and the intense heating near perihelion. And it's a thermal management system, absorbing heat that might otherwise create detectable infrared signatures. The composition would naturally match local chemistry because the probe gathered most of its ice during approach, mixing it with whatever primordial ice it carried from its origin. The cyanogen and carbon compounds detected in 3I/Atlas? Simple. Molecules, easily incorporated. Cyanogen is just carbon and nitrogen, two of the most common elements in the universe. Diatomic carbon forms readily in low-temperature, low-pressure environments, like interstellar space or cometary surfaces. Water ice? Literally everywhere. Nothing exotic, nothing unusual. The genius isn't in creating exotic materials. It's in hiding artificial components beneath layers of completely ordinary, natural-looking material that conveniently burns away as the probe passes through the system, revealing nothing. Detection and measurement capabilities present interesting engineering challenges, but nothing insoluble. How does a probe encased in ice observe its surroundings? Several approaches work. Carefully positioned sensors that remain covered until needed, then expose themselves briefly during optimal observation windows. Small openings in the ice shell, perhaps disguised as naturally occurring vents or cracks. Ice that's deliberately transparent at specific wavelengths. Pure water ice transmits radio frequencies easily. A probe could monitor radio emissions from the target civilization, detect broadcasts, measure transmitter power, analyze content, all while appearing to be a simple comet. The ice is transparent to exactly the frequencies you care about. Passive observation during the approach phase, before the ice shell becomes opaque with accumulated dust and impurities. During the years or decades of approach, while still in the outer solar system, conduct most observations. By the time you pass through the inner system where human detection is most likely, switch to passive mode, letting the natural sublimation process proceed without active systems that might be detected. Data storage requires no exotic technology. We currently store information at densities exceeding 1 terabyte per cubic centimeter, using three-dimensional storage media and molecular scale recording techniques. A probe the size of 3I/Atlas 9, 160 meters in diameter, roughly 500,000 cubic meters of volume, could store an unimaginable amount of data. Everything it observes during its passage could be recorded for later retrieval or transmission. Communication back to the home civilization presents the trickiest challenge. Radio signals travel at light speed, so transmitting from our solar system back to an origin point hundreds of light years away would take centuries for the signal to arrive. Real-time communication is impossible over interstellar distances. The laws of physics simply don't permit it. But several approaches could work. Directional laser communication. A tightly focused laser beam, pointed precisely toward the home system, could transmit enormous amounts of data at light speed. The beam divergence would be minimal. Most of the signal would travel in the intended direction. From Earth, detecting such a beam would require looking in exactly the right direction, at exactly the right wavelength, at exactly the right time. Miss any of those, and the transmission is invisible. Store everything and transmit later. Perhaps the probe doesn't communicate in real time at all. It stores all observations internally, completes its pass through the target system, then continues to a rendezvous point where a larger vessel retrieves it. Or it waits until it's far enough from the target system deep in interstellar space, where transmissions are unlikely to be detected, then sends its data package. Quantum entanglement communication remains theoretical for us, likely to remain so. Entangled particles are correlated, but you can't transmit information faster than light using that correlation, at least not according to current understanding of quantum mechanics. But perhaps advanced civilizations have found approaches we haven't imagined. It's the one area where genuinely new physics might be required. Or, and this is an intriguing possibility, perhaps the probe doesn't need to communicate at all. Perhaps its entire purpose is local observation, gathering data about our civilization's technological threshold. Did we detect it? Did we correctly identify it as interstellar? How quickly did we respond? What instruments did we use? All of that is observable from the probe's perspective. Watching our observatories point in its direction, monitoring our communications about its discovery. That data alone, confirmation that this civilization has reached detection threshold, might be all the information the probe needs to collect. Mission accomplished simply by being detected. Power requirements are entirely manageable with current understanding. Radioisotope thermoelectric generators, RTGs, have powered deep space probes for decades. Voyager 1 and Voyager 2, launched in 1977, are still operating after 45 years using RTGs. The devices are simple, elegant. Radioactive material decays, producing heat. Thermocouples convert temperature difference into electricity. No moving parts, no maintenance required. Reliable for decades or centuries. A probe designed for interstellar travel would likely use more efficient versions, perhaps radioisotopes with longer half-lives, perhaps more advanced thermocouple materials. But the principle is proven technology for us. For an advanced civilization, it would be trivial. During cruise phase, the centuries of travel between stars, power needs are minimal. Most systems dormant, only basic monitoring active. A small RTG could provide sufficient power indefinitely. Near the target star, power requirements increase for active observations and potential communication. But solar panels can supplement stored power, hidden beneath sublimating ice until needed, then exposed as the ice naturally vaporizes. From an external observer's perspective, nothing looks artificial, just exposed surfaces as the comet ablates naturally. Trajectory control is subtle but achievable using entirely natural-looking mechanisms. A probe approaching a solar system can use gravitational assists from outer planets to adjust its path. This is standard technique. We use it routinely for our own spacecraft. New Horizons used a Jupiter gravity assist to reach Pluto faster. Voyager probes used multiple planetary assists to tour the outer solar system. The physics is well understood. The technique is proven. Small course corrections early in the trajectory produce large effects on final approach geometry. By the time Earth-based observers detect the object, it's following a purely ballistic path. No active propulsion needed, just momentum and gravity. If 3I/Atlas made course corrections, They would have occurred years or decades before discovery, while the object was still in the outer solar system, too far and too faint for our telescopes to detect. Outgassing provides another mechanism for subtle trajectory adjustment. By controlling which surface areas sublime, perhaps using beneath-surface heaters to trigger ice vaporization at specific locations, you create thrust vectoring. It looks completely natural. Comets do this constantly through purely natural heating variations, but if you're clever, you can use it for deliberate course adjustments, hidden within the noise of natural cometary behavior. Here's what makes this scenario genuinely plausible, what moves it from science fiction to science. We can see ourselves developing this technology within the foreseeable future. Not decades, perhaps, but within centuries? Absolutely. If human civilization survives and continues technological development, we will likely send probes to other star systems within 500 to 1,000 years. The engineering challenges are substantial but not insurmountable. We're already designing concepts, Breakthrough Starshot, Project Dragonfly, various NASA studies that could achieve interstellar travel using physics we understand today, and we're already having ethical discussions about how to approach other civilizations if we detect them. Should we attempt contact? Should we observe quietly first? Should we avoid disrupting less technologically advanced species? These debates are happening now, in academic circles, in SETI working groups, in philosophical discussions about our responsibilities as a potentially spacefaring civilization. The consensus emerging from these discussions leans toward caution. If we detect a civilization less advanced than ourselves, most ethical frameworks suggest we should observe without interfering. We should gather information about their technological level, their social structures, and their development. We should avoid imposing ourselves on their history, their evolution, their natural progression. If that's our conclusion, reached through careful ethical reasoning, why wouldn't other civilizations reach similar conclusions? Why wouldn't they develop protocols for studying emerging species without disrupting them? And if you're studying an emerging civilization, if you want to measure their technological capabilities without revealing yourself, what better method than sending a probe disguised as a natural object? If they detect it and correctly identify it as interstellar, they've demonstrated significant capability. If they don't, they're not ready yet. Either way, you've gathered crucial data without interference. We'll likely disguise our probes to some degree, both to protect them during the journey. Encasing them in ice provides excellent shielding against cosmic radiation and micrometeorite impacts, and to avoid alarming civilizations we encounter. We've already discussed this in the context of our own future missions. If we can envision doing it within centuries, others probably have done it already. The galaxy is billions of years old. Stars have been forming planets for most of that time. If intelligence emerges even occasionally, if even a small fraction of intelligent, the species develop technology and survive long enough to achieve interstellar capability, then there should be civilizations out there millions of years ahead of us. What we're struggling to develop, they perfected long ago. The physics permits it. Einstein's relativity allows speeds up to light speed. You can't reach or exceed it, but you can achieve significant fractions of it with enough energy. Nothing about the disguise mechanism violates physical law. Nothing about the observation and data storage requirements exceeds what we can already imagine building. The engineering is challenging, but it's engineering, not magic. It's sophisticated application of known principles, not speculation about unknown physics. The motivation is clear: gathering information about other civilizations without interfering. We understand that motivation because we share it. We want to know if we're alone. We want to understand our cosmic context. If we detected another civilization, especially one less advanced than ourselves, we'd want to study them carefully, thoughtfully, with consideration for their development. Why wouldn't others do the same? The test hypothesis doesn't require believing in impossibilities. It requires accepting that if intelligence is common in the galaxy, and the sheer number of planets suggests it might be, then some of those intelligences will have developed technology comparable to what we're approaching. They'll have applied that technology to interstellar exploration. They'll have developed methods for studying emerging civilizations, and they'll occasionally send probes through systems like ours, gathering data, measuring capabilities, assessing readiness. Whether 3I/Atlas was such a probe remains unknown. The data doesn't prove it. But the data doesn't rule it out either. And crucially, the mechanism by which it could be such a probe isn't mysterious or magical. It's engineering. Advanced engineering, certainly. Engineering beyond our current capabilities, but engineering nonetheless. Engineering based on physics we understand, principles we've already proven, technologies we're already developing ourselves. That's perhaps the most profound realization from examining these mechanics carefully. The test hypothesis doesn't require us to believe in something impossible. It requires us to believe that others might have achieved what we can already see ourselves achieving in the future. And if that's true, if other civilizations have developed the technology we're developing, applied it to purposes we're considering, sent probes through stellar systems, using methods we can envision, then 3I/Atlas might have been exactly what some astronomers quietly suspect, a test disguised as a comet, measuring our capabilities, assessing our readiness. The universe suddenly becomes far more interesting, not because new physics emerges, but because engineering we can imagine might already have been implemented by others who had a few million years head start. It's not about believing in magic. It's about recognizing that what looks like magic to us might simply be engineering to them. And that's a profound shift in perspective, one that makes the test hypothesis not impossible speculation, but uncomfortable possibility. The next interstellar visitor is already en route. Right now, somewhere in the vast darkness between stars, another object is approaching our solar system, or will be soon. We don't know when it will arrive tomorrow, next year, next decade. We can't predict its trajectory or timing because we don't know where it's coming from or how fast it's traveling. But it's coming. The statistics make this clear. Based on the detection rate from Oumuamua and 3I/Atlas, we should expect more. Perhaps several per year once our detection systems reach full capability. Perhaps dozens per year if the interstellar population is denser than current models suggest. The question isn't whether we'll detect more interstellar objects. The question is what we'll do when we detect them, how we'll study them, how we'll finally, definitively determine if any are artificial, and whether we'll be ready this time. The Vera C. Rubin Observatory in Chile represents the next revolution in detection capability. The facility sits atop Cerro Pachón, a mountain in the Chilean Andes chosen for its exceptional astronomical conditions. Clear skies, minimal light pollution, stable atmosphere, everything needed for serious observation. The telescope itself features an 8.4-meter primary mirror, large but not record-breaking. What makes Rubin revolutionary isn't mirror size, it's the camera. The largest digital camera ever constructed for astronomy, 3.2 gigapixels. For comparison, a high-end smartphone camera captures about 12 megapixels. Rubin's camera captures 3,200 megapixels in a single image. More important than resolution is the survey strategy. Rubin will photograph the entire visible sky every 3 to 4 nights, creating a constantly updated map of everything that moves or changes. Every asteroid, every comet, every variable star, every supernova, and critically for our story, every interstellar object passing through our solar system. The facility is scheduled to begin full operations in 2025, with the Legacy Survey of Space and Time LSST running for 10 years. Current estimates suggest Rubin will detect between 1 and 10 interstellar objects annually once the survey reaches full efficiency, perhaps dozens per year if the population density is higher than models predict. Think about what that means. Right now, we have 2 confirmed interstellar detections over 8 years. Within a decade, we might have 50 or 100. Within 2 decades, perhaps hundreds. This flood of detections will finally provide statistical data we currently lack. 2 data points tell us almost nothing about distributions, patterns, or typical characteristics. You can't do meaningful statistics with 2 examples. 10 data points start revealing patterns. Which trajectories are common? Which compositions appear frequently? Which behaviors are typical? 50 or 100 data points. Now we can do real science. We'll see whether trajectories are randomly distributed or show clustering. We'll compare compositions across multiple objects. Are they all similar, like 3I/Atlas, or diverse as expected from objects originating in different stellar systems with different formation chemistries? We'll measure size distributions, rotation rates, outgassing patterns, everything. Patterns will emerge from the noise, and those patterns will either support natural explanations or demand new thinking. If interstellar objects arrive from uniformly distributed directions with diverse compositions and behaviors entirely explicable through natural processes, the test hypothesis becomes untenable. The natural explanation wins decisively. But if patterns emerge, if trajectories cluster toward the ecliptic plane where Earth-based detection is optimal, if compositions are suspiciously uniform, if detection rates correlate with our technological development, then we'll need to reconsider. Detection is just the first step, though. Study requires different capabilities, different technologies, different approaches entirely. The European Space Agency's Comet Interceptor mission represents humanity's first attempt at a rapid response system for studying fleeting targets. Currently scheduled for 2029 launch aboard the Ariane 6 rocket, this mission embodies lessons learned from 3I/Atlas. Here's how it works. The spacecraft launches not toward any specific target, but toward a parking orbit. Specifically, the Sun-Earth L2 Lagrange point a gravitationally stable location, approximately 1.5 million kilometers from Earth, on the side away from the Sun diat. This location, gravitational forces from the Sun and Earth balance in a way that allows objects to maintain position with minimal fuel expenditure. There, the spacecraft waits. Systems dormant to conserve fuel and extend operational lifetime. Solar panels provide minimal power for basic monitoring and communication. Instruments remain off, propellant reserves carefully managed, but it's watching. Ground-based telescopes, Rubin Observatory, other survey systems continuously scan the sky. When they detect a promising target, a long-period comet making its first passage through the inner solar system, or, ideally, an interstellar object analysis begins immediately. Trajectory calculations determine whether intercept is possible. How much fuel would it require? What's the optimal intercept geometry? How much warning time exists before the target becomes too distant? The European Space Agency convenes decision panels. Scientists evaluate the scientific case. Engineers assess technical feasibility. Mission managers consider fuel budgets and operational constraints. If the decision is go, if the target is sufficiently compelling, and intercept is achievable, Comet Interceptor activates. The spacecraft separates into 3 components: a main probe, approximately 1 meter across, and 2 smaller subprobes roughly half that size. They target different intercept trajectories, approaching the object from different angles. This multi-probe approach provides redundancy if one fails, others continue, and multiple perspectives, allowing 3-dimensional reconstruction of the target. Each probe carries instruments specifically designed for close-up cometry study, cameras for high-resolution imaging, capable of resolving surface features down to meter scale, spectrometers for composition analysis, measuring not just what chemicals are present but their spatial distribution across the surface, magnetometers, for detecting magnetic fields that might reveal internal structure. Dust analyzers for examining particles ejected from the surface, determining composition, size, distribution, and velocity. Plasma instruments for studying how the object interacts with the solar wind. Everything designed for rapid deployment, quick intercept, maximum science return from a brief encounter. Now imagine this scenario playing out. It's 2032. The Vera Rubin Observatory detects an object with hyperbolic orbit, eccentricity greater than 1.0, definitively interstellar. Initial observations suggest closest approach in 8 months. Trajectory brings it within 2 astronomical units of the Sun, optimal for detailed study. Comet interceptor, waiting patiently at L2 for 3 years, receives targeting data. Mission control at the European Space Operations Center in Darmstadt, Germany, calculates intercept solutions. Multiple trajectories are possible depending on fuel budget and desired encounter geometry. The decision goes forward. This is what the mission was built for. Authorization proceeds through ESA hierarchy. Final trajectory selected. Execution approved. Comet interceptor fires its main engines, departing L2. The spacecraft is now committed. It will intercept this target or use all its fuel trying. There are no second chances once fuel is spent. The mission ends. Months of cruise follow. The spacecraft and target both moving, both adjusting trajectories slightly through minor thruster burns, converging on a predetermined intercept point in space and time. Ground controllers monitor constantly. Trajectory refinements occur weekly, then daily, then hourly as encounter approaches. Then the moment arrives. The 3 spacecraft components, having separated days earlier to target different approach vectors, sweep past the interstellar visitor at relative velocities of several kilometers per second. The encounter lasts minutes, maybe 10, maybe 20, depending on geometry. But those minutes could answer questions that have haunted us since 3I/Atlas. Cameras capture images, not fuzzy blurs from billions of kilometers away, but actual resolved surface features. The texture of the surface, the distribution of ice versus rock, the presence or absence of geometric patterns. What might those images show? If the object is natural, we'd expect irregular surface sculpted by billions of years of cosmic radiation exposure. Impact craters from micrometeorites, random fracture patterns from thermal stress. Surface features distributed chaotically, shaped by natural processes over geological timescales. The composition would match natural formation ice and rock in proportions consistent with cometary origin, isotope ratios, typical of whatever stellar system ejected it. No anomalies, no surprises. Natural explanation confirmed decisively. The test hypothesis refuted by direct observation. Case closed. But if the object is artificial, the images might reveal something entirely different. Geometric patterns too regular for natural formation. Straight edges where natural objects should show curves. Right angles where erosion should have rounded everything. Repeated structures suggesting purposeful arrangement rather than random accretion. Or perhaps nothing obvious on the surface, the disguise perfect. The ice shell genuinely natural looking, but instruments detect anomalies beneath. Mass concentrations inconsistent with natural ice and rock distribution. Dense regions suggesting metal or composite materials hidden inside. The gravitational field subtly wrong for a natural object of that size and apparent composition. Temperature anomalies could tell the story. Infrared sensors detect hotspots, localized temperature elevations, inconsistent with solar heating alone. Internal power sources generating waste heat, carefully managed but detectable at close range with sensitive instruments. Magnetic field measurements might reveal organization. Natural objects have weak, chaotic magnetic fields, frozen in magnetism from their formation, oriented randomly. Artificial objects might show structured fields, deliberate arrangements, suggesting active systems, power generation, or data storage using magnetic media. Radio emissions at specific frequencies would be extraordinary. Natural objects don't broadcast. They emit thermal radiation, blackbody radiation, determined purely by temperature, but not modulated signals at discrete frequencies. Detection of structured radio emissions, even weak ones, would be nearly definitive evidence of artificiality. Any of these would be extraordinary. Any would demand follow-up, deeper investigation, international coordination to determine what we've actually found. The protocols for announcing such a discovery are surprisingly underdeveloped. The SETI community has established post-detection protocols for radio signals. The Declaration of Principles Concerning Activities following the detection of extraterrestrial intelligence, established by the International Academy of Astronautics. It provides guidelines for verification, announcement, and international coordination if we detect signals from another civilization. But physical artifacts? The protocols are vaguer, less formalized. The process would likely unfold something like this. The mission team verifies data integrity first. Are the instruments functioning correctly? Could this be an error, a malfunction, a misinterpretation? They check calibrations, review telemetry, examine every possible source of false positive. If anomalies persist, if multiple instruments confirm unusual findings, expert panels convene. Scientists not directly involved with the mission review the data independently. Can they reproduce the analysis? Do they reach the same conclusions? The scrutiny is intense. Careers depend on getting this right. If the conclusion holds, if genuine anomalies inconsistent with natural formation persist through every level, of verification information passes to space agency leadership. At ESA headquarters, at partner agencies worldwide, discussions begin. How do we announce this? What do we say? When? Coordinated announcement through multiple channels becomes essential. Scientific papers submitted simultaneously to major journals, Nature, Science, Astrophysical Journal, providing detailed technical analysis. Press conferences at space agencies presenting findings to public audiences, briefings to government officials explaining implications. But in our hyper-connected world, controlling information flow is nearly impossible. Mission scientists have families. They have colleagues. They have social networks, personal relationships, professional connections. A discovery this profound would leak almost immediately through informal channels. A worried email to a spouse. We found something. I can't tell you what, but it's big. That spouse mentions it to a friend who works in journalism. Speculation begins. An excited phone call between colleagues. Have you seen the interceptor data? This doesn't look natural. Word spreads through the astronomical community within hours. Oblique references at conferences. Cryptic social media posts. Unusual activity at space agencies noticed by observant journalists. By the time official announcement arrives, the world already knows something extraordinary is happening. Social media explodes with speculation. News organizations chase sources. The announcement confirms what's already spreading through human networks at the speed of information. What happens after announcement depends entirely on what's found. If the object is clearly artificial but inactive, perhaps a derelict probe from a long-dead civilization, the technology that functioned millions of years ago but failed during its interstellar journey, focus shifts to study and potential recovery. Could we capture it, bring it back for detailed laboratory analysis? The engineering challenges would be immense. The object is moving at interstellar velocities, tens of kilometers per second relative to our Sunday. Matching velocities, rendezvousing, capturing, and returning, it would require propulsion capabilities we barely possess. But the scientific value would be incalculable. Proof of extraterrestrial technology, available for direct examination. Every government with space capability would want involvement. Every space agency would propose missions. International cooperation, sharing costs, sharing data, sharing discoveries would make sense. But geopolitical competition would also emerge. Who gets to study it first? Who controls access? Who owns the technology recovered from it? Probably both simultaneously. International cooperation on some aspects, national competition on others, treaties negotiated, agreements established. Conflict over details inevitable. If the object appears artificial and active, still functioning, still collecting data, perhaps still transmitting, the situation becomes far more complex. Is it communicating? Ground-based radio telescopes would monitor continuously, searching for signals. If it's transmitting towards some distant star system, we might detect those transmissions. Analyzing them, determining frequency, modulation, content, would become an international priority. Should we attempt communication ourselves? This question creates profound disagreement. Some argue we should try, hail the probe, attempt to establish contact, send mathematical sequences or scientific information that might elicit response. Others argue for caution. We don't know who built it, what their intentions are, whether contact would be beneficial or harmful. The SETI protocols assume communication with distant civilizations, messages taking years or decades to travel between stars. But a probe in our solar system could receive and respond within hours. Real-time conversation becomes possible. What do we say? How do we say it? Who speaks for humanity? These aren't idle questions. They're scenarios scientists and policymakers are beginning to consider seriously. Not because anyone believes 3I/Atlas was artificial, most remain skeptical, but because the possibility demands preparation. We don't want to be improvising protocols in the moment of discovery. Discussions are happening now. Working groups at NASA consider scenarios and responses. ESA convenes panels to establish procedures. The United Nations Office for Outer Space Affairs holds sessions on peaceful uses of space and international cooperation in extraterrestrial contact. Slowly, carefully, frameworks are being built. Not because we expect to use them soon. Most participants consider it unlikely, but because being unprepared would be inexcusable. Meanwhile, ground-based observation capabilities continue improving dramatically. The extremely large telescope in Chile, currently under construction with a 39.3-meter primary mirror, will achieve first light in the late 2020s. That mirror diameter is almost 5 times larger than current record holders. Light-gathering power scales with mirror area, so ELT will collect almost 25 times more light than 8-meter class telescopes. What can you do with that much light-gathering power? Observe fainter objects, resolve finer details, conduct spectroscopy on targets currently too dim for detailed analysis. An interstellar object detected by Rubin could be studied by ELT with unprecedented detail, even at the vast distances where Hubble struggled with 3I/Atlas. The James Webb Space Telescope, already operational since 2022, observes at infrared wavelengths, where internal heat signatures would be most visible. If an interstellar object contains active systems generating waste heat, Webb might detect thermal anomalies invisible to optical telescopes. The Square Kilometre Array, a radio telescope, currently under construction in Australia and South Africa, featuring thousands of individual antennas working together, will monitor vast swaths of sky continuously for radio emissions. If an interstellar object transmits, SKA will likely detect it. The Nancy Grace Roman Space Telescope, scheduled for late 2020's launch, will conduct wide-field infrared surveys, complementing Rubin's optical observations. Between Rubin and Roman, we'll have nearly complete coverage of objects moving through the inner solar system. This growing network of instruments creates multiple overlapping detection and analysis capabilities. An interstellar object arriving in the 2030s will face scrutiny impossible in 2019. Multiple telescopes tracking from discovery. Coordinated observation campaigns planned in advance, not scrambled together reactively. Rapid response missions like Comet Interceptor ready to deploy. Analysis frameworks prepared to identify anomalies systematically. We're building the infrastructure to definitively answer questions that 3I/Atlas only raised. The timeline matters profoundly. If interstellar objects arrive at rates suggested by post-Oumuamua models, several per year, once detection is optimal, we'll have dozens of examples by the mid-2030s. Statistical patterns will emerge clearly from that sample size. If the test hypothesis has merit, certain indicators should appear. Trajectory biases toward the ecliptic plane, where Earth-based detection is most probable. Timing correlations with our technological development detection rates increasing as our capabilities improve. Perhaps composition uniformity suggesting common origin or construction. Behaviors that persistently resist natural explanation despite intense scrutiny. If it's purely natural, we should see opposite patterns. Random trajectory distribution, showing no preference for any particular approach angle. Diverse compositions reflecting different stellar systems, with different formation chemistry. Detection rates stable or increasing only proportionally to improved telescope sensitivity. Every behavior explicable through conventional physics. Either answer is profound. Either changes how we understand our place in the universe. If natural, we've discovered that interstellar space is far more dynamic than previously imagined. Material exchange between stellar systems is common enough that we regularly detect objects traversing our neighborhood. The implications for planet formation, chemical evolution, and potentially even panspermia life spreading between worlds or natural objects are revolutionary. We're not isolated. The galaxy actively shares material across vast distances. If artificial, we've confirmed we're not alone. Intelligence exists elsewhere. Technology exists elsewhere. The galaxy contains civilizations capable of interstellar engineering. That's arguably the most important discovery humanity could make. Everything changes our self-perception, our place in cosmic context, our understanding of life's prevalence and intelligence's inevitability. The waiting is perhaps the strangest part of this story. We know more visitors are coming. We know when detection capability reaches full potential. Rubin at full survey cadence, Roman scanning infrared wavelengths, ground-based facilities coordinated will spot them regularly. We're preparing tools to study them thoroughly. We're developing frameworks to interpret findings. We're establishing protocols for response, but we can't force the timeline. Nature, or whoever sent them, operates on schedules beyond our control. All we can do is watch. Wait. Stay ready. The next chapter is being written now, in the darkness between stars. Objects are traveling toward us, natural wanderers or purposeful probes, we don't yet know. But when they arrive, we'll be watching. We'll be ready to gather data, analyze findings, determine truth, and maybe we'll get the clearer evidence that transforms uncomfortable hypothesis into definitive knowledge. We'll learn whether we're alone or accompanied, whether we're being tested or simply observing natural processes, whether 3I/Atlas was an anomaly or a harbinger. The universe holds these answers. We're building the tools to read them. Within our lifetimes, we might know for certain. The next interstellar visitor could be the one that tells us. It might already be approaching, and this time we'll be ready. As you settle into sleep, let's return to where we began, that moment in August 2019 when telescopes caught something impossible, an object from another star, visiting briefly, then departing forever. In the months since its discovery, 3I/Atlas has traveled an unimaginable distance. It passed beyond Neptune's orbit months ago, beyond Pluto, beyond the classical Kuiper Belt where New Horizons encountered Arakoth, that distant, pristine relic of solar system formation. By now, in October 2025, 6 years after discovery, it's crossed deep into the scattered disk, that vast region where the sun's influence begins to fade. Out there, where sunlight is 100 million times dimmer than we experience on Earth, where temperatures hover just a few degrees above absolute zero, where the space between objects is measured not in millions but in billions of kilometers. No telescope on Earth can see it anymore. The distance is too great, the object too small, the reflected sunlight too faint. Even if we pointed Hubble directly at its predicted position, even if we exposed for hours, collecting every possible photon, we'd see nothing. Just the blank darkness of space. Just the distant stars forming their familiar patterns, unchanged by this invisible visitor passing between them. It's too far, too faint, just another invisible dot among trillions. It has become, once again, what it was before we detected it. Part of the three. Interstellar background. A wanderer in the dark. It's going home, or continuing its mission, or simply drifting, as it has for eons, through the silent dark between stars. We'll never know for certain what 3I/Atlas truly was. The data we collected, while extensive by the standards of 2019, leaves too many possibilities open, too many questions unanswered, too many gaps in our observations where crucial information might have hidden. Natural comet from another stellar system? Almost certainly yes, by conventional measures. By Occam's razor, the principle that simpler explanations are generally preferable to complex ones, natural origin wins. It looks like a comet. It behaves like a comet. Its composition matches comets we've observed thousands of times. The straightforward interpretation is that it is a comet, just one that formed around another star and was ejected into interstellar space by gravitational interactions billions of years ago. But that, almost certainly, is where mystery lives. That qualifier almost represents the space between what we know and what we can prove, the gap between data and certainty. The timing doesn't feel random. 2 interstellar objects within 3 years, after millennia of none. The trajectory doesn't feel random, both visitors approaching through similar geometries, both crossing the ecliptic plane where Earth-based detection is optimal. The composition doesn't feel random, 2 perfectly matching solar system comets, too familiar, too normal. These observations don't prove artificial origin. They don't even strongly suggest it. But they create space for doubt. Not certainty of artificiality, but impossibility of certainty regarding naturalness. Sometimes, the absence of proof either way is itself an answer. We don't know enough yet. We're not ready yet. Our technology crossed the threshold of detection. We can spot these visitors now, identify them, track them, but we haven't yet crossed the threshold of understanding. We can see them, but we can't definitively determine what they truly are. Perhaps that's the test. Not whether we detect interstellar visitors at all, but whether we're mature enough as a civilization to acknowledge uncertainty without demanding premature conclusions. Whether we can sit with mystery, continuing to gather evidence patiently, without either dismissing possibilities reflexively or accepting them without proof. If 3I/Atlas was sent to test us, perhaps we're still taking that test now, in how we respond to ambiguous data, in how we prepare for future observations, in how we think about the question of extraterrestrial intelligence, in whether we can maintain scientific rigor while remaining open to extraordinary possibilities. Think about what we've learned regardless of 3I/Atlas's true nature. Think about the thresholds we've crossed simply by detecting it. We've learned that material travels between stars regularly enough that we can detect it. This wasn't guaranteed. Before Oumuamua, interstellar objects were purely theoretical. We assumed they existed based on models of stellar formation and gravitational ejection, but we'd never observed one. Now we know for certain the galaxy is more connected than we imagined. Material flows between stellar systems. Objects journey for millions of years through interstellar space, occasionally passing through neighborhoods like ours. We've learned our models of the galaxy were incomplete. The predicted detection rates were wrong off by large factors in ways we're still trying to understand. Either the interstellar population is denser than we thought, or ejection rates are higher, or our detection capabilities improved faster than models anticipated. Whatever the explanation, reality surprised us. The universe works differently than our calculations suggested. We've learned we have the technology to spot these visitors, track their trajectories, analyze their compositions from billions of kilometers away. This capability is new, just a decade old, for reliable, systematic detection. But it's real. We're no longer blind to the interstellar medium flowing through our cosmic neighborhood. We can see what we couldn't see before. That alone represents a threshold crossed, a capability achieved, a new era of astronomy beginning, and we've learned to ask new questions. Not just what is this object, but could this object be artificial? A decade ago, most astronomers would have dismissed that question immediately. Unscientific, inappropriate, bordering on pseudoscience. The kind of question that damages careers and credibility. Today, it's a legitimate inquiry, debated at conferences, addressed in peer-reviewed papers, incorporated into mission planning for future observations. Major astronomical institutions design protocols for detecting and responding to potential artificial objects, not because they expect to find them, but because the question has become scientifically valid. The question itself changes how we observe, what we look for, how we interpret data. Even if no interstellar visitor ever proves artificial, asking the question makes us better observers, more careful analysts, less prone to dismissing anomalies as unimportant, more willing to consider uncomfortable possibilities. Perhaps the test isn't about detecting the probes at all. Perhaps it's about learning to think in new ways, learning to balance skepticism with openness, maintaining scientific rigor while acknowledging that the universe might contain surprises our current frameworks don't anticipate. Learning to prepare for discoveries that would fundamentally change our understanding of our place in the cosmos, not assuming they'll happen, but not assuming they can't. Learning to sit with uncertainty, to say, we don't know yet, without feeling that represents failure. Recognizing it as the honest state of knowledge, at a frontier where observations outpace understanding. If 3I/Atlas was sent to test us, perhaps the test is ongoing. Perhaps it's not about whether we detected the object we did, but about what we do with that detection, how we respond to ambiguity, how we prepare for the next visitor, how we think about questions that were unthinkable a generation ago. The romantic interpretation holds that we're being watched, monitored by civilizations far older than ours, civilizations that have navigated the challenges we're facing: technological development, environmental sustainability, social cohesion, the transition from planetary to interstellar species. They send probes disguised as natural objects, measuring our responses, assessing our readiness. When we demonstrate we can detect interstellar visitors, identify them correctly, study them scientifically, without either panic or dismissal, maybe then we receive clearer signals. Maybe then we're contacted more directly. Maybe 3I/Atlas was the first step in a longer process of introduction, first contact proceeding gradually rather than dramatically, testing before teaching, observing before engaging. In this interpretation, we pass the first threshold by detecting the object. We're being evaluated on subsequent thresholds: how we handle uncertainty, how we prepare for future encounters, whether we develop the maturity necessary for beneficial contact with civilizations whose technology and perspective might be profoundly alien to our experience. The skeptical interpretation holds that we're pattern-seeking creatures desperate for meaning in random events. We spotted 2 interstellar objects in quick succession through a combination of improved technology and statistical chance. Our models underestimated population density, a failure of calculation, not evidence of design. Our minds evolved to find patterns even in noise, construct narratives of purpose and intention where none exists. We see faces in clouds, hear voices in static, perceive design in randomness. The test hypothesis reflects our psychological needs, our hopes about cosmic companionship, our fears about cosmic loneliness, more than any evidence in the data. We want to believe we're being watched because the alternative that we're utterly alone in an indifferent universe, that consciousness arose exactly once in cosmic history, that we bear sole responsibility for preserving intelligence in a galaxy that would otherwise contain none, feels unbearable. So we construct scenarios where we're not alone, where others watch over us, where our struggles have cosmic significance because someone else cares about the outcome. In this interpretation, 3I/Atlas was exactly what it appeared to be. A natural comet from another star system, interesting scientifically, but ultimately just rock and ice following ballistic trajectory through our neighborhood before returning to the void. Nothing more. The timing is coincidence. The trajectory is chance. The perfect normalcy is simply what natural objects look like. Both interpretations are valid. Both are supportable with current evidence. Both are intellectually honest positions based on the same data set. That's okay. That's how science often works at the frontiers where observations challenge existing frameworks. Science doesn't always provide clean answers immediately. Sometimes it says, we need more data. Sometimes it says, check back in a decade. Sometimes it acknowledges that multiple interpretations remain viable until additional evidence narrows possibilities. The beauty of the scientific method is that it's patient, iterative, self-correcting. We don't have to know everything now. We don't have to choose between interpretations prematurely. We just have to keep observing, keep questioning, keep refining our understanding as new data arrives. Eventually, perhaps soon, perhaps not for decades, we'll have enough information to choose definitively, enough interstellar objects detected to establish statistical patterns, enough close-up observations to determine composition and structure unambiguously, enough evidence to prove natural origin or demonstrate artificiality beyond reasonable doubt. Until then, we live with mystery, and honestly, there's something beautiful about that. As you drift towards sleep, imagine that object, the one we called 3I/Atlas. Imagine it as it travels now through the outermost reaches of our solar system, where the sun is just another star, barely distinguishable from the others except by knowing where to look. Imagine it as it truly might be, 960 meters of ice and rock, surface sculpted by 1 billion years of cosmic radiation, pitted by micrometeorite impacts, colored by complex organic molecules synthesized slowly through radiation chemistry, ejected from another star system during that system's youth, when planets were forming and gravitational chaos ruled, wandering ever since through the galaxy, alone in the dark, following a path determined by physics and chance, occasionally passing through stellar systems but never stopping, never captured, always moving, a natural object, a cosmic wanderer, a piece of another world carrying the chemical signature of its birth but no consciousness, no purpose, no mission beyond continuing to exist and move according to laws of motion established at its ejection billions of years ago. Or imagine it differently. Imagine it as sophisticated machinery encased in camouflaging ice. Sensors that recorded everything during its brief pass through our solar system, our radio emissions, our satellite constellations, our atmospheric composition, our response to its detection. Data stored in molecular-scale memory systems, preserved for retrieval or transmission. Power systems managing waste heat carefully, maintaining temperature profiles indistinguishable from natural solar heating. Course control systems dormant now, having accomplished their mission, guiding the object precisely through the target zone before returning to ballistic drift. Now transmitting, perhaps. A tightly focused laser beam pointed towards some distant star system, carrying compressed data about this civilization that detected an interstellar visitor for the second time in its history, or waiting to transmit until it's farther from the target system, safer from detection, or storing everything internally, continuing to a rendezvous point where another vessel will retrieve it centuries from now. Artificial, purposeful. A test successfully completed, data gathered, mission accomplished. Both images are equally valid based on what we know. Both accord with observations. Both explain the data we collected. We can't distinguish between them with certainty, not with measurements taken from billions of kilometers away, not with the brief observation window we had. Both spark wonder. Both represent profound truths about the universe, just different truths. If natural, we live in a galaxy where material flows freely between stellar systems, where chemistry from one star's planets can journey to another, where nothing is truly isolated. The cosmos is more dynamic, more connected, more interesting than we imagined. We're part of a vast ecosystem of stellar systems exchanging material constantly, and we're finally developing the tools to observe that exchange. If artificial, we live in a galaxy populated by intelligence, by consciousness that arose independently on other worlds, by civilizations that developed technology and directed it toward interstellar exploration. We're not alone. We're not the first. Others preceded us, developed capabilities we're still struggling toward, and they're watching, measuring, assessing, perhaps preparing for eventual contact. The cosmos contains not just matter and energy, but minds, purposes, intentions. Either answer reshapes everything. Either represents one of the most profound realizations our species could achieve. The next visitor is already coming. Maybe it's still light years away, decades from arrival, a faint dot in some distant stellar system beginning its journey toward ours. Maybe it's closer years away, already in interstellar space between stars, following a path calculated long ago by processes we don't yet understand. Maybe it will arrive next month, sudden and surprising like its predecessors, giving us no time to prepare beyond what we've already prepared. Whenever it comes, we'll be more ready than we were for 3I/Atlas, more telescopes watching, Rubin Observatory at full survey cadence, scanning the entire sky every few nights, Roman Space Telescope conducting infrared surveys, ground-based facilities coordinated internationally, ready to respond within hours of detection, better detection algorithms running continuously, trained on data from Oumuamua and 3I/Atlas, optimized to spot hyperbolic trajectories and flag them immediately for human review, rapid response missions prepared to launch, Comet Interceptor waiting at L2, fuel reserves managed carefully, ready to deploy on short notice when a compelling target appears. Scientists worldwide coordinated through established networks, communication channels already open, observation protocols already written, analysis frameworks already tested. And maybe, just maybe, we'll get the clearer evidence that transforms hypothesis into knowledge. We'll capture high-resolution images showing either natural features or geometric patterns. We'll detect either thermal signatures matching natural heating or anomalous hotspots suggesting internal power. We'll measure either random magnetic fields or organized structures. We'll observe either pure ballistic motion or subtle course corrections. Something definitive, something that resolves uncertainty, something that tells us, finally, what these visitors truly are. Until then, we live with mystery. We live with wonder. And honestly, there's something profound about living in this particular moment in human history. We're the first generation to routinely detect interstellar visitors. Our ancestors watched the sky for millennia, tracking planets, noting comets, mapping stars, but they never saw what we can see. They couldn't detect objects from other stellar systems passing through ours. That capability didn't exist. Future generations will likely have answers we don't have. They'll have detected dozens or hundreds of these objects. They'll have statistical patterns we lack. They'll have close-up observations we couldn't make. They'll know things we can only speculate about. But we live in the threshold moment, the transition between blindness and sight, between wondering and knowing, between speculation and evidence. We're pioneers, witnesses to a new chapter in humanity's cosmic story. The first people ever to see interstellar visitors and recognize them for what they are. The first to ask whether we're being tested. The first to build infrastructure specifically designed to answer that question. That's remarkable. That's profound. That's worth pausing to appreciate, even as we acknowledge how much we still don't know. Sleep well, knowing the universe is larger than previous generations imagined. Larger, stranger, more connected, more dynamic, possibly more populated. Sleep well, knowing we're watching now. Our telescopes scan the sky continuously. Our detection algorithms flag unusual objects automatically. Our protocols for response improve yearly. We're ready for whatever comes next. Sleep well, knowing that somewhere in the darkness between stars, objects are traveling toward us, carrying mysteries we'll eventually solve, bearing answers to questions that have haunted us since we first looked up and wondered if we're alone. Whether they're natural or artificial almost doesn't matter in a strange way. The fact that we can ask the question that we can, imagine both possibilities, prepare to test both hypotheses, to gather evidence to choose between them, means we've crossed a threshold as a species. We're ready to know. We're ready to discover. We're ready for the universe to reveal its secrets, whatever they may be. Maybe those secrets confirm we're alone, the only consciousness in a vast but empty cosmos, bearing special responsibility to preserve and spread intelligence because we're the only ones who have it. Maybe those secrets confirm we're accompanied, sharing the galaxy with other minds, other perspectives, other civilizations that navigated the challenges we're facing and emerged to explore the cosmos. Either way, we'll handle it. Either way, we'll adapt. Either way, we'll continue doing what we do, asking questions, gathering evidence, seeking truth, building understanding incrementally through patient observation and careful analysis. The story of 3I/ATLAS isn't finished. It's just beginning. That object still travels outward, invisible now, but still there, still moving, still carrying whatever secrets it holds. In centuries, it will be farther from the sun than any human-made spacecraft has traveled. In millennia, it will cross into interstellar space proper, becoming once again what it was before we detected it. A wanderer in the dark, part of the cosmic background of objects flowing between stellar systems. But it changed us. By visiting, by being detected, by raising questions, we can't yet answer. It changed how we think about our place in the cosmos. It made us wonder, made us prepare, made us ready for the next visitor and whatever revelations it brings. And somewhere out there, the next one approaches. Maybe natural, maybe not, but definitely coming. When it arrives, we'll be watching, we'll be ready, and maybe finally we'll learn the truth about what these mysterious visitors truly are. Until then, rest easy. The mystery continues. The wonder persists. The universe keeps its secrets a little longer, and that's okay. That's part of the beauty of discovery. The questions are sometimes as valuable as the answers. The story continues. The next chapter waits to be written, and we're here to witness it all unfold. Sweet dreams.